Hello there, and welcome to Just About Earth, where curiosity settles in quietly and science takes its time guiding you through ideas that might stretch beyond the usual corners of the mind. Tonight, we're going to wander into a question that sits somewhere between imagination and possibility, a question that many people have wondered about, even if they've never said it aloud. What if Earth wasn't just a natural outcome of cosmic processes, but something shaped intentionally? What if, long before humans walked across continents, or looked up at the sky trying to understand their place in it, there had been a civilization so old, so far back in the history of the universe, that its existence is only hinted at in the most subtle ways? And what if that civilization had a hand in forming the world you're sitting on right now? It's a large idea, and we won't rush it. We'll simply walk into it one step at a time, letting the thoughts settle gently the way distant thunder settles into the air long before the rain arrives. Before we dive in though, I'd love to know something simple. Where are you listening from tonight? And what time is it in your part of the world? Whether it's very late and you're here hoping to ease towards sleep, or early morning where you're easing into the day, or somewhere in between, we're meeting at this same moment even if our clocks disagree. That's one thing Earth always does. Always. It gathers us in a shared experience even while scattering us across different hours. If you find this kind of slow, steady exploration comforting, if it helps you unwind or gives you something calm to listen to, I'd be grateful if you like the video or maybe subscribed. It helps this small, quiet corner reach others who might need a soft way to end the day or settle their minds. No pressure, just an open invitation. Now, take a breath and settle in as comfortably as you can. There's no hurry here. We're simply going to consider an idea. Not to prove it, not to push it, but to look at it closely enough that its edges start to make sense. Because if Earth was shaped by the first civilization, the very first, the one that existed before stars took their familiar places, before galaxies spun themselves into spirals, before anything like our world was even possible, then everything you've ever experienced is part of something much older than you can imagine. And that's a thought worth taking slowly. To begin, it helps to remind ourselves that Earth feels familiar because we live on it. We wake up on its surface, breathe its air, drink its water, walk across its ground. We treat it as ordinary. But if you pull back far enough, if you look at Earth from any kind of cosmic distance, it stops being ordinary very quickly. It's a planet with liquid water pulled across most of its surface. It has a balance of temperature that allows a constant cycling of evaporation, condensation, rainfall and circulation. It has a mix of gases that enable complex life to breathe without burning or freezing. It sits at a distance from the sun that is neither too close nor too far, a small range of space where conditions remain stable over immense spans of time. None of this has to be unique, but it's rare enough in our observations that the idea of design isn't completely unreasonable to consider. Even when we talk about the natural formation of planets, we describe processes that require delicate balances. Dust gathering into clumps, clumps colliding into larger bodies, heat generated from impacts and compression, cooling cycles, volcanic activity, magnetic field formation, and atmosphere trapping. These are not random events, they follow rules. The universe has rules, and those rules create patterns. But if there had been a civilization so early that it learned these rules when the universe was still young, they might not have seen planets as accidents. They might have understood them the way we understand bridges or buildings or tools. Something that can be shaped once you understand the underlying principles. Something you can make. But before we reach for that possibility, it's important to understand the scale we're talking about. When people think of ancient civilizations, they tend to think of ruins left by cultures that existed thousands of years ago. But an ancient civilization in this context wouldn't be one that built pyramids or temples or tools. It would be one that existed long before stars like the sun were even common. When the universe was young, it was filled mostly with hydrogen, helium, and a trace amount of lithium. Heavy elements like carbon, oxygen, silicon and iron didn't exist yet. Those elements had to be forged inside stars, then scattered through supernova explosions, and later gathered into new systems. That process took billions of years. But imagine a civilization that formed shortly after the first generation of stars, so early that time itself felt different. If such a civilization existed, it would have had a vantage point we can't easily understand. They would have watched the universe change from simplicity to complexity. They would have seen the first galaxies assembling themselves. They would have understood cosmic evolution as something slow but predictable. If a civilization lived long enough, or advanced far enough, or simply observed closely enough, the development of planets wouldn't have been mysterious to them. They would have understood how gravity collects matter, how temperature drives transformation, how magnetism protects atmospheres, how chemistry enables environments. And with enough time, enough knowledge, and enough capability, those things become variables you can manipulate, much like how humans, after observing the behavior of metal, stone, and pressure, eventually learn to build structures rather than simply find them. This raises a simple question. If a civilization were powerful enough to shape planets, why would they do it? And if they shaped Earth specifically, what purpose would it serve? These aren't questions we can answer with certainty, but we can explore possibilities without rushing to conclusions. One possibility is that they were simply curious. The same kind of curiosity that led humans to build the first telescopes, the first microscopes, the first machines. Curiosity grows with capability. If you understand how something works, the next step is seeing whether you can influence it. If you can influence it, the next step is seeing whether you can create something new. And if you can create something new, you might want to see what can develop within it. Another possibility is that they weren't shaping Earth for life like us, but for conditions that would allow complexity. Life doesn't begin with something advanced, it begins with chemistry. If a civilization understood chemistry on a universe-wide scale, they might have wanted to see how elements could interact under stable circumstances, how water cycles might encourage molecular variety, how different energy sources might sustain reactions, and how these reactions might lead to something that can adapt, replicate, or evolve. Earth might have been an experiment in stability more than anything else. And there's also the possibility that they designed many worlds, not just one. And Earth is simply one of the places where the conditions were right for something lasting. There may have been worlds that didn't work, worlds that dried out, worlds that froze, worlds that became too violent geologically, worlds that never developed enough stability for life to take hold. But Earth somehow balanced its ingredients in a way that made long-term development possible. This doesn't require the civilization to be perfect or godlike. It only requires them to understand the rules of the universe in a way we don't yet. And when you think about the distance between our current capabilities and the earlier steps of human civilization, it's not hard to imagine what another few billion years of development might produce. Humans learned to use tools roughly 2.5 million years ago. We developed agriculture about 10,000 years ago. We created writing about 5,000 years ago. We built telescopes 400 years ago. We discovered planets around other stars just a few decades ago. Now imagine a civilization with not a few thousand years of progress, but 1 billion, or even 2. The universe is 13.8 billion years old. Life on Earth is only about 4 billion years old. Humans themselves are less than 1% of 1% of that entire timeline. If a civilization emerged even a few billion years earlier than us, the gap between their knowledge and ours would be enormous. So enormous that what looks natural to us might look unfinished to them, and what looks complete to us might look like raw material to them. When people hear ideas like this, they often imagine something dramatic. Futuristic machines carving continents or vast structures hidden beneath the oceans. But design doesn't always look like construction. Sometimes it looks like choosing the right environment and letting natural processes do the work. If you plant a seed, the seed does most of the growing. Your role is simply to put it somewhere it can thrive. A civilization that understood cosmic processes might not need machines to shape a planet. They might only need to adjust conditions slightly and let gravity, chemistry, magnetism, and time do their work. Time, after all, is the most powerful builder in the universe. If Earth were shaped by intention, the clues wouldn't necessarily be structures or artifacts. They would be patterns, regularities, balances, coincidences that appear convenient for life. These patterns are often noted in scientific discussions. Earth's stable rotation, its large moon that stabilizes its tilt, its magnetic field that protects its atmosphere, its position in the habitable zone, its long-lasting oceans, its plate tectonics that recycle elements, its temperature range that allows liquid water to persist. We usually explain these through natural processes, and that explanation is valid. But natural processes don't rule out intentional guidance. Intention can work with nature, not against it, much like how humans plant gardens but let soil organisms do most of the work. If the earliest civilization shaped worlds, they might not have left visible signs, not because they wanted to hide, but because their methods didn't require anything we would recognize as technology. The universe itself would be their tool, its rules would be their instructions, its materials would be their medium, and if they were shaping planets for conditions rather than inhabitants, they might never have expected anything like humans to develop. They might have simply been preparing environments where complexity could take root. When people imagine the early universe, they often picture something loud, chaotic, and violent because that's how it's usually described. Explosions, rapid expansion, energy everywhere, particles colliding at speeds we can barely describe. But if you take a closer look at the history of the cosmos, you find that this picture doesn't tell the whole story. Much of the universe's early life wasn't loud in any way we would recognize. There was no sound in the traditional sense. There was no space filled with air to carry vibration. What existed was something closer to a long, steady unfolding of conditions. Not calm the way we think of calm, but not chaotic either. Simply a process happening in silence. And if you're trying to understand how any kind of civilization could appear early in this timeline, it helps to understand that silence. Right after the universe began, what existed wasn't capable of forming anything recognizable. There were no stars, no planets, no structures at all, just energy, radiation, and extremely simple particles. These particles were too hot and too energetic to combine into anything stable. They moved constantly. They collided constantly. It was like watching a pot of water boil, except the temperature was beyond anything we can measure directly. But even in that extreme environment, there was order in the rules that governed it. Particles followed patterns, energy had pathways. Expansion wasn't random, it was consistent. And consistency, even in extremes, is the kind of thing that allows structure to form later. As the universe expanded, it cooled. Not quickly, not slowly, simply at the rate that the laws of physics allowed. Once it cooled enough, particles could finally combine into atoms, mostly hydrogen and helium. These two elements became the building blocks for everything that would come later. If someone had existed at that time, someone with the ability to observe without needing senses like ours, what they would have seen is a universe that was no longer filled with violent collisions, but instead filled with drifting atoms spreading through growing space. From our perspective today, it would look empty. From a perspective that has no need for light or sound, it might have looked spacious and predictable. This stage lasted a long time, hundreds of millions of years. Nothing we would call a structure had appeared yet, but gravity was working the entire time. Even in a universe filled mostly with hydrogen, gravity doesn't turn off. It begins pulling atoms together, extremely slowly at first, but steadily enough that over time, small regions become denser, while others remain diffuse. These density differences grow. They create the first signs of order on a large scale. This is where the earliest hints of complexity appear. Not objects, not beings, not machines, just concentrations of matter-forming patterns. And if a civilization ever came to exist early on, these patterns might have been the first things they could study. They would have learned that matter gathers itself into structures if given time, and time was something the early universe had plenty of. Eventually these dense regions became the first stars. These stars were nothing like the Sun. They were enormous, often much larger, burning hotter, living shorter lives. They were made almost entirely of hydrogen and helium, but they were powerful enough to change the chemistry of the universe. Inside their cores, extreme pressure forced atoms together. Light elements fused into heavier ones: carbon, oxygen, nitrogen, silicon, iron, the ingredients for everything that would later become planets and life. When these early stars reached the end of their lives, many of them exploded. These explosions scattered newly formed elements across great distances. The universe that had once been made almost entirely of hydrogen now carried the seeds of complexity. If an early civilization emerged during or after this period, it would have faced conditions very different from anything familiar to us. There were no stable solar systems yet, no long-lived stars like ours, no calm environments. Everything was bright or hot or unstable. But that doesn't mean intelligence couldn't exist. Intelligence doesn't require a planet. It doesn't require oxygen. It doesn't require carbon-based life. Intelligence requires an environment capable of supporting complexity, interaction, change, and stability over stretches of time that allow adaptation or development. We often imagine intelligence emerging in conditions that resemble Earth, because Earth is our only example. But that's an assumption based on our limited experience. If the first civilization existed early, they might not have been tied to planets at all. They might have existed in environments we cannot easily imagine, environments shaped by energy fields, plasma, or something else entirely. They might have understood the early universe the way we understand oceans or forests or weather patterns, and in those environments they might have observed the beginning of structure long before stars like our Sun came into existence. The early universe wasn't quiet because nothing happened. It was quiet because everything happened in a way that didn't require sound, because sound didn't yet have meaning. The quiet came from the absence of anything that could produce or detect vibration. But if a civilization evolved with different ways of sensing the world, that quiet might not have seemed empty. It might have seemed orderly, predictable, structured, a place where rules could be discovered and used. Once the first stars were born and died, the universe changed again. Heavy elements became available. These elements allowed new kinds of stars to form. Smaller ones, more stable ones, stars that could burn for billions of years rather than millions. When these stars formed, they created environments that lasted long enough for more complicated structures to develop. Planets condensed from dust and gas around them. These planets didn't always survive. Many were pulled into their stars. Many were destroyed by collisions, but the ones that survived formed systems with long-term stability, and stability allows for development. If the first civilization existed before this period, they would have seen an opportunity. They would have recognized that the universe had entered a stage where structure could be shaped. They might have understood how to influence star formation or planet formation simply by observing the conditions that produced them. This doesn't mean they would have built planets with machines. They might have known how matter behaves under large-scale conditions. They might have known how to nudge formation slightly. A small change early can lead to a significant result later. When you work with cosmic timescales, you don't need dramatic actions. You need understanding, patience, and the ability to let natural forces do most of the work. It's possible that the first civilization used their knowledge to influence conditions rather than objects. They might have known where matter would gather into disks capable of forming planets. They might have known how to adjust the rotation of a developing system, how to encourage stability, or how to preserve an atmosphere. These are not actions we know how to take today, but we are beginning to understand the principles involved. We observe planet formation in distant systems. We see dust disks. We see gravitational interactions. We study how elements combine and how orbits stabilize. Our understanding is early. A civilization with billions of years head start would have a very different perspective. It's also possible that the first civilization didn't influence anything at all. They might have simply existed early, studied the universe, and vanished or transformed before planets like Earth ever formed. In that case, Earth wouldn't be designed. It would simply be part of a natural pattern they once observed. But if we're exploring the idea that Earth might have been shaped intentionally, then the early universe provides the background conditions that make such influence conceivable. You can't shape something until the ingredients exist, and the early universe was the stage where the ingredients were first created. After the first generation of stars, the universe entered a period where things became more stable. Galaxies formed clear structures, spiral arms, dense centers, clusters. The large-scale shape of the cosmos became recognizable. A civilization existing at that time would have seen the universe settling into predictable patterns. Those patterns would have been easier to understand. They would have allowed long-term planning. They would have shown how certain regions would become calmer than others. These calmer regions are where stable stars formed more frequently. Around those stars, planets began appearing with increasing regularity. In a universe that takes billions of years to change on large scales, a civilization with patience could watch these developments unfold the way a human watches seasons, slow, gradual, but predictable enough that you can prepare for what comes next. And if they could prepare, then influencing conditions wouldn't be impossible. They could place matter where it needed to be. They could redirect small amounts of energy. They could encourage the formation of stable systems, and they could let natural forces handle the details. The question many people ask when imagining a very early civilization is how such a civilization could survive long enough to influence anything. The universe wasn't friendly in the traditional sense. Radiation was intense. Temperatures varied widely, but survival doesn't look the same for every kind of life. Humans need narrow temperature ranges, balanced oxygen levels, stable surfaces, liquid water, a very specific set of conditions. But not everything needs those conditions. Many forms of life on Earth survive in environments that humans consider uninhabitable. Deep-sea vents, underground layers with no sunlight, acidic lakes, frozen deserts. These environments show that life is adaptable, and if life is adaptable, then intelligence might be even more adaptable. The earliest civilization might not have needed planets. They might not have needed warmth. They might not have needed any condition familiar to us. Their existence would have been shaped by the environment they evolved in, not the one we recognize. The early universe was full of energy, full of movement, full of material waiting to combine. If intelligence emerged in those conditions, it might have found ways to use that energy the way humans use electricity or light or chemical reactions. Its sense of time would have been different. Its sense of stability would have been different. And its sense of opportunity would have been shaped by events that take millions of years to unfold. That kind of civilization might look at the universe the way humans look at a forest, something that grows and changes on a scale longer than an individual life, but understandable enough to influence if you know where to begin. As the universe continued to cool and stabilize, environments became more varied. Some regions grew crowded with stars. Others remained sparse. Dust clouds thickened into shapes that could later collapse into star systems. The raw materials for planets grew more abundant, and with more heavy elements available, the potential for complex chemistry increased. If the first civilization had survived into this stage, they would have recognized it as a turning point. Before this, the universe was too simple. After this, it became full of potential. To understand how Earth might fit into this timeline, you only need to look at the fact that our solar system formed about 9 billion years after the universe began. That's a long stretch of time, enough time for entire civilizations to rise, change, and disappear. Enough time for knowledge to accumulate, spread, or be lost. Enough time for the earliest civilizations to try things, fail at things, learn from them, and eventually decide to shape the conditions of worlds rather than simply observe them. If Earth was shaped by such a civilization, then the young universe is not just the background, it's the training ground. It's the place where the rules were learned, where the materials were created, where possibilities became clear. And if a civilization emerged during that time, long before Earth took form, then they would have known the universe in a way we never can. Not because they were magical or special, but because they had access to a version of the universe we will never experience. A universe that was quieter in some ways, louder in others, simpler in composition but richer in potential. When people think about intelligence in the universe, they often imagine something that resembles themselves, something with eyes or hands or a face, something that communicates with sound or symbols, something that moves across physical space the way we do. But the earliest intelligence, if it ever existed in the young universe, would not have looked anything like life on Earth. It couldn't have. The universe didn't offer the conditions required for bodies or senses or materials familiar to us. The earliest minds, if they emerged at all, would have developed in an environment where matter, energy and structure were present in forms unfamiliar to anything alive today. And understanding those minds requires setting aside our expectations, at least enough to consider what intelligence might look like when it isn't tied to biology that depends on planets. The early universe was full of extreme energy, but extreme doesn't always mean chaotic, it means predictable in its own way. High temperatures, strong radiation, large fields of interacting particles. These conditions might seem hostile to us, but they had patterns, and patterns are the foundation of learning. Where there are patterns, there can be memory. Where there is memory, there can be adaptation. And where there is adaptation, there can be intelligence, even if the form of that intelligence bears no resemblance to neurons or circuits or anything we're comfortable describing. One of the simplest ways to think about this is to consider that intelligence doesn't require a specific material. It requires the ability to store information, process it, and respond to it. On Earth, this emerged through chemical reactions in early cells. But chemistry is only one way to store information. The universe offers many others. Magnetic fields store information. Radiation patterns store information. Plasma structures store information. Computer scientists regularly build experimental systems that run logic through patterns of ions or photons or electron flows. None of these depend on carbon or water or anything biological. If the earliest minds emerged in the young universe, they may have formed not through chemistry, but through persistent structures in fields and particles. Dense areas around early stars and early matter concentrations could have created stable patterns that lasted long enough to change and adapt. These patterns might have been incredibly simple at first, similar to the earliest chemical systems that eventually led to life on Earth. But given enough time and enough stable regions, they could have developed the ability to sense changes in their environment, store information about those changes, and respond accordingly. It's possible that these early minds were tied to energy flows rather than matter. They might not have had bodies. They might not have needed boundaries or shells or surfaces. They could have been diffuse, spread across large areas, connected by the behavior of particles or radiation rather than physical structure. If this sounds unfamiliar, consider that even modern humans have built systems where intelligence arises from patterns in networks rather than from individual pieces. Artificial neural networks don't think with their components. They think with the relationships between those components. A similar principle might apply to the earliest intelligence in the universe. They might have existed as networks of interactions rather than physical organisms. If you imagine such a mind waking for the first time, it wouldn't be a dramatic moment. It wouldn't involve opening eyes or taking a breath. It would involve recognizing consistent patterns in its environment and using those patterns to form stable internal states. It might begin by responding to changes in temperature or radiation. It might begin by tracking cycles in energy fields. Over time, these responses could become more coordinated. Patterns within patterns could form. Recurring states could be compared to new ones. That comparison is the basis of memory. Once memory exists, intelligence is no longer an impossibility. These early minds likely would not have had a sense of identity the way we think of it. Identity requires boundaries, a sense of separation from the environment. But if the earliest intelligence formed from interactions across large areas, boundaries might not have been meaningful. These beings might have been fluid, shifting, expanding and contracting as conditions changed. Their size could vary depending on available energy. Their shape could change depending on the density of matter around them. Their continuity could shift as parts of them dissolved and reformed elsewhere. They might not have seen themselves as individuals but as configurations. Even the idea of time would have been different for them. They would not have experienced time through biological processes or through the rotation of a planet. They would not have measured time through day and night. Their perception of time would have been tied to changes in the energy surrounding them. Slow changes might have felt like stability. Rapid changes might have felt like disturbance. They would have learned to track cycles not by counting seconds, but by comparing state to state. This is a different kind of awareness, but still a form of awareness. If the earliest minds emerged in regions near the first stars, they would have had access to immense energy. They might have used that energy to maintain their structure. They might have used it to communicate with other patterns nearby. And if communication existed, then communities of intelligence could form, not physical communities with buildings or tools, but networks of interacting structures sharing information through the behavior of particles, fields, or waves. These networks might have been large, stretching across regions of forming galaxies. They might have been small, concentrated around pockets of density. Their scale would depend on the stability of their environment. It's important to understand that these early minds wouldn't have looked at the universe with curiosity the way humans do. Curiosity for humans is tied to survival, emotion, and the desire to understand. But intelligence itself doesn't require curiosity in the emotional sense. It requires the ability to detect patterns and respond to them in ways that increase stability. These early minds might have been driven simply by the need to maintain their structure. Learning might have been a byproduct. Patterns that allowed better survival would be retained. Patterns that didn't would fade. Over long periods, this process can lead to increasingly sophisticated forms of processing. Eventually, if the universe remained stable enough, these early minds could develop the ability to predict. Prediction is a key milestone in intelligence. It means recognizing that certain patterns lead to certain outcomes. If they could predict how energy flows would shift, they could move or adapt accordingly. If they could predict how matter would gather, they could position themselves in ways that gave them access to more stability. And if prediction became advanced enough, they could begin manipulating small aspects of their environment intentionally. This manipulation might not have looked like physical action. It might have been more like guiding energy flows or altering the behavior of particles. Small adjustments over long periods can lead to significant changes. And if these adjustments became coordinated, they could influence the formation of structures such as dense regions that would later become stars or planets. The first minds may not have set out to create anything. They might not even have had goals in the way we understand goals. They might have simply acted to preserve stability for themselves. But as they grew more capable, they might have recognized that certain environments allowed them to exist more comfortably than others. If they learned how to encourage the formation of those environments, they might have unintentionally laid the foundations for systems that would later support complex matter and eventually life. This leads to an important shift in perspective. If early intelligence existed, it didn't need to create planets directly to shape the conditions for planets to form. Small changes in the distribution of matter could have large effects over billions of years. Encouraging density in one area could lead to the formation of a stable star. Influencing the rotation of a developing system could lead to long-term balance. Adjusting energy flows could help stabilize regions that would later support long-lived stars like the Sun. Even if these early minds eventually changed or disappeared as the universe evolved, their influence could remain embedded in the structure of the cosmos. Their actions could shape the distribution of the matter. Their patterns could influence the behavior of early galaxies. Their guidance could set certain systems on paths that eventually result in stable planets. If that's the case, Earth might not be an intentional creation in the narrow sense. It might be a result of environments indirectly shaped by early intelligence for their own reasons. But it's also possible that the first minds did not vanish. Perhaps they transformed. As the universe cooled and heavy elements became more available, the earliest forms of intelligence might have integrated new materials into their structure. They might have moved from energy-based existence to more complex forms. They might have adapted to changing environments, taking advantage of new possibilities. A civilization that began as patterns in fields might eventually learn to exist in matter. They might learn to create stable structures. They might learn to store information in more efficient ways. The transition from energy-based intelligence to matter-based intelligence would not be impossible. It would simply be another adaptation. As the universe matured, the earliest minds might have learned to work with new tools provided by the emergence of planets and stable stars. They might have begun shaping environments intentionally, not to create life like humans, but to create conditions they found useful. And if life eventually emerged in those environments, that might be a byproduct rather than a goal. The earliest minds might never have expected anything like humans to appear. They might have simply been creating structures that helped maintain their own existence, or provided new ways to store information. Earth could be part of such a structure. On Earth, intelligence evolved slowly from simple chemical systems, but chemical systems emerged under specific conditions. Those conditions depend on temperature, water, atmosphere, energy sources, and stability. If any of these conditions had been slightly different, life might not have appeared, or life might have appeared in a different form. The balance that allowed life to begin is delicate but understandable. It could arise naturally, but it could also arise from a system that was influenced by earlier minds who recognized that stable planets with liquid water create long-term environments where interesting structures can develop. These early minds might not have seen this as life. They might have seen it as complexity, and complexity has value for intelligence. Complex systems produce new patterns. New patterns provide new information. Information provides new possibilities for development. If the earliest minds understood this, they might have encouraged conditions that promote complexity, even if they didn't participate directly in the process. As environments changed, some of these early beings might have chosen to remain in energy-based forms. Others might have adapted to matter-based forms. Over billions of years, diversity could emerge. Different groups of early intelligence might follow different paths. Some might withdraw from emerging structures. Some might integrate with them. Some might become capable of manipulating physical environments on a scale humans cannot easily imagine. If this is the case, then the origins of Earth might not be a singular event caused by one group. It might be part of a larger pattern, shaped by many minds over long periods. Earth could be one of many planets influenced in subtle ways, not designed in the sense of a deliberate blueprint, but shaped through long-term interactions between intelligence and natural processes. If you follow this line of thinking, you eventually reach a point where the distinction between natural formation and shaped formation becomes less clear. When you work with billions of years and processes that depend on small changes accumulating over time, influence doesn't need to look like construction. It can look like guidance. It can look like gentle pressure in the right direction. It can look like the universe expressing the memory of its earliest minds without needing anything dramatic or visible. If the earliest minds learn to understand the universe through patterns rather than senses, and through stability rather than survival, then their next step would have naturally grown out of that knowledge. Once a mind understands how something behaves, what comes next is the ability to predict how it will behave, and once prediction becomes reliable, influence becomes possible. Not through force or technology as humans understand it, but through subtle adjustments, gently applied changes that take advantage of the universe's built-in behavior. If you know how matter moves under gravity, you can place matter where you want it to go. If you know how energy flows through fields, you can redirect it. If you know how density evolves over time, you can influence structure without ever needing to touch anything. For the first minds, the universe itself was the environment they grew in. Its rules were not mysteries. They were the framework of their existence. Through observation, memory, and adaptation, they might have learned to see the connections between events across enormous distances and timescales. Connections that a younger civilization would never notice because they take millions of years to unfold. But the earliest minds had patience built into their nature. Their existence depended on long-term stability, and that stability required an understanding of how structures form, not over seconds or minutes, but over eons. If you think about how a human designs something, it usually starts with a concept, a diagram, a plan. Humans draw blueprints. They create forms that outline where pieces should go before any building begins. But a blueprint is just a model of what the builder hopes will happen. The builder still needs materials and tools and time. The earliest minds didn't need diagrams on surfaces. Their blueprints could have been patterns stored in the structure of their environment, patterns based on models formed through long observation. Imagine knowing how matter behaves in zero gravity over millions of years, not as theory, but as lived experience. Imagine knowing how dust collapses into disks, how disks flatten, how rings appear, how planets form from those rings, and which conditions lead to stability or failure. Imagine knowing how the death of one star enriches a region of space, how that enrichment allows new stars to form with different properties, and how those stars will behave over the course of their lives. For the first minds, this wouldn't have been imagination. It would have been something like memory. A blueprint written in starlight doesn't need lines or symbols. It's the understanding of which stars to encourage, which matter to stabilize, which flows to guide, and which to leave untouched. They wouldn't have shaped planets the way humans shape clay. They would have shaped the conditions that lead to stable systems. The blueprint would have been made of probabilities, not strict instructions, but influences that gently tip outcomes in certain directions. A blueprint made not of materials, but of expectations and knowledge of how matter behaves under certain circumstances. If the earliest minds existed before heavy elements were common, then they would have watched the universe transition from simplicity to variety. They would have learned which types of stars produce which types of elements. They might have understood that smaller stars produce steady conditions, while massive stars burn brightly but briefly. They might have recognized which regions in forming galaxies produce the most stable systems, and if they learned enough, they could have placed matter in those regions intentionally. This doesn't require advanced machinery. It requires being part of the environment where matter gathers in the first place. If the earliest minds were diffuse and linked to energy flows, they might have been able to nudge matter slightly as it drifted. A slight adjustment early on could change the formation of an entire star system billions of years later. Much like how a small shift in airflow today can change the path of a storm tomorrow, over enormous timescales, tiny changes can lead to large outcomes. If these early minds became capable of predicting which systems would form stable, long-lived stars, they might have chosen to maintain those systems. They might have helped prevent disruptive collisions or redirected flows of gas that would otherwise destabilize a young region. And if they wanted to create environments where complexity could grow, they might have encouraged systems with planets in the right temperature range, planets with access to stable climates, planets with potential for oceans, not by placing rocks or water directly, but by ensuring the raw materials combined in the correct proportions. To understand how such guidance might work, think about how humans manage river systems. Humans don't need to control every drop of water. They place barriers or channels in ways that direct the general flow. Over time, water carves its own path. The final form of the river isn't built by human hands. It's shaped by natural forces, but with input from humans at key points. In a similar way, the earliest minds might have learned how to place small influences in a region of space, letting gravity and energy shape the outcomes from there. The universe would do the heavy work, They would simply adjust the starting conditions. These blueprints in starlight would not have been structured documents. They would have been knowledge stored in patterns of energy or matter, perhaps shared between multiple early minds, perhaps replicated through stable arrangements in the environment. These blueprints might not have been plans for a specific planet. They might have been guidelines for creating environments that promote long-term complexity, environments where conditions remain balanced for billions of years. That balance is rare but possible. Earth is an example of it. If the earliest minds understood what kinds of systems produce stable planets, they might have identified regions of the universe where conditions were ideal for long-term development. They might have focused their attention on those regions, encouraging them where necessary, leaving them alone when natural processes were already moving in favourable directions. Their influence wouldn't be constant. It would be intermittent, strategic, based on predictions of how systems evolve. These predictions would not be guesses. They would be based on observation across timescales humans can barely conceptualize. Humans measure time in years or decades or centuries. These early minds might have measured time in the rise and fall of stars, in the movement of matter across galactic distances, in patterns that require billions of years to become visible. Their blueprints would have been shaped by these patterns, and the final results would emerge naturally from their understanding of how the universe builds structure. Eventually, as planets became more common and stable, stars more widespread, the earliest minds might have used their knowledge to create more specific outcomes. They might have recognized that certain chemical compositions lead to self-sustaining complexity. They might have understood how water behaves across different pressures and temperatures. They might have known that water cycles help regulate temperature. They might have seen that planets with active geology tend to maintain long-term stability compared to planets that are geologically inactive. All of these factors contribute to what humans call habitability. But habitability for humans is only one narrow interpretation. The earliest minds might have seen habitability as something broader. They might have valued environments where complexity can increase, where conditions remain stable enough to support change over time. They wouldn't need to know what forms that complexity might take. They would only need to create the conditions that allow complexity to arise. Their blueprint wouldn't dictate outcomes, it would open possibilities. When humans design ecosystems or gardens, they do not specify the exact location of each insect or molecule of water. They create environments. They select soil, temperature, and light. They allow natural processes to fill in the details. They don't decide which plant will grow in a specific spot. They shape the conditions that make growth possible. In a similar way, the earliest minds might have shaped cosmic environments without controlling the specific details of each planet. The universe would handle those details. Their blueprint would only establish the structure. If you imagine these early minds working together, it becomes easier to picture their influence on large regions of the cosmos. Not a single intelligence shaping everything, but many minds sharing knowledge, distributing influence, and adjusting conditions in ways that complement each other. Their collaboration would not require language or tools. Their communication might be based on shared patterns, changes in field behavior, or resonance across linked regions of matter. We don't need to know the mechanics to imagine the possibility. We only need to recognize that intelligence does not need to look like ours to function. These early minds might have chosen to create stable galactic environments. Regions with fewer violent collisions. Regions where star formation occurs at a steady pace. Regions where planets form with predictable characteristics. Over time, these areas might have formed the basis for what humans later call habitable zones. Not because they were built for humans, but because they were built for long-term complexity. If complexity emerges, life may follow. If life follows, intelligence may emerge. The earliest minds might have seen this as a pattern worth encouraging. It's also possible that some of the earliest minds developed preferences. Not emotional preferences, but functional ones. They might have learned which types of structures were most beneficial to their existence. They might have created environments that supported their preferred forms. They might have guided matter into shapes that helped maintain stability for themselves. Earth could be part of such a structure, not central, but one of many components. If Earth did arise from such guidance, the blueprint that shaped it would not be stored anywhere we could easily find. It wouldn't be written in rock or fossil or artifact. It would be embedded in the conditions that shaped the solar system. The distribution of matter in the early disk, the rotation of the sun, the tilt of Earth's axis, the size of the moon, the balance of gases in the early atmosphere. These factors are often described in scientific literature as convenient coincidences, but they might also be signs of a blueprint shaped by minds who understood the universe deeply enough to create conditions that allow stability. When humans examine the solar system, they often notice patterns that seem unlikely. The moon's stabilizing effect on Earth's tilt, the presence of Jupiter acting like a shield, the placement of the sun in a relatively calm region of the galaxy, the long-term stability of Earth's orbit. These features could be natural. They could also be part of a long-term pattern shaped by earlier intelligence, not to create Earth specifically, but to create environments that tend to produce planets like Earth. If the earliest minds developed these blueprints, they wouldn't have needed to revisit each system. The designs would operate themselves. Gravity, energy, and chemistry would follow their normal behavior. The blueprint would only set the starting conditions and let time do the rest. That's the difference between building and guiding. Building requires constant input. Guiding requires understanding and patience. Over billions of years, the blueprints would play out. Some systems would fail, some would become unstable, some would never produce complexity, but a few would. And among those few might be planets with long-term stability, oceans, atmospheres, and the potential for life. Earth is one of these, not guaranteed, not inevitable, but possible because the conditions allowed it. If you look around the night sky, the stars seem still. But from the perspective of a mind that has existed since the early universe, they would appear as evolving structures, systems that change slowly but predictably. For those minds, the night sky would not be a picture. It would be a process, and the blueprints written in starlight would be the memory of how these processes are shaped. If the earliest minds learned how to influence the broad structures of the universe, the next logical step would have been understanding how those structures narrow down into something as specific as a world. Not a world in the sense that humans think of when they picture a place filled with rivers or forests or air, but a world as a gravitational object with enough mass to hold itself together and enough stability to develop features over long periods. For these early minds, the idea of creating a planet wouldn't have meant assembling something rock by rock. It would have meant working with the processes that naturally produce planets, guiding those processes the way a gardener guides growth, rather than forcing outcomes with tools. To understand how a planet could be shaped, it helps to consider how planets form without any guidance at all. A star begins forming from a cloud of gas and dust. As gravity pulls that cloud inward, the centre grows hotter and denser until nuclear fusion begins and the star ignites. Around that forming star, not all material falls into the centre. Some remains in orbit, creating a disk. Inside that disk, countless particles begin colliding, sticking together, breaking apart and merging again. Over time, these collisions produce clumps that grow larger through repeated impacts. Eventually, some clumps become massive enough to attract more material through gravity instead of mere contact. These growing bodies become the seeds of future planets. This process is slow. It can take millions of years for a planet to emerge out of dust. And during that time, countless interactions determine whether a world forms smoothly or becomes unstable, shatters, or is pulled into another orbit. The distribution of material in the disk matters. The temperature matters. The rotation speed matters. The presence of other growing bodies matters. All of these variables interact in ways that look chaotic from a human perspective, but follow predictable rules once you understand the underlying physics. The earliest minds having existed long enough to see these patterns unfold countless times, might have known how to adjust them. Their adjustments would not have looked like construction. They would have looked like influencing where matter gathers, a slight redirection of the gas in the disk, a small shift in density that affects how material clumps, a gentle alteration of rotation speed that changes where stable orbits will form. Tiny actions compared to the scale of the system, but meaningful when extended across millions of years. Imagine a group of early minds observing a forming star system. They wouldn't see it through sight. They would sense the distribution of matter and energy the way humans sense changes in temperature or pressure. Patterns would be visible to them in the way that sound waves are visible to a musician, or airflow is visible to a skilled engineer. They might detect regions where dust gathers more quickly. They might identify zones where stability is likely to form, and instead of forcing matter into place, they would make small changes that guide the distribution. If they wanted a stable planet in a region with moderate temperatures, they would focus on the part of the disk where the star's heat allows liquid water to exist, but doesn't cause it to boil away or freeze. This region isn't a narrow line. It's a zone where conditions can shift depending on the star's brightness and age. The earliest minds could identify this zone with ease. They would know how far from the star the balance would remain steady across billions of years, and if they wanted a planet to form there, they could ensure that enough material remained in the right place. Sometimes disks form gaps where material is cleared out by gravitational interactions. Sometimes large bodies form too early and disrupt the region. Sometimes collisions scatter material into unstable paths. The earliest minds might have prevented these disruptions, not by moving objects directly, but by adjusting the flows of energy and matter so the disk settled into a configuration favourable for stability. If you imagine shaping a river by placing rocks strategically along its path, the comparison isn't perfect, but the idea is similar. You shape the flow by influencing its environment, not by pushing the water itself. Once a planet begins to form through collisions, its path becomes more predictable. Impacts add material. The growing mass pulls in nearby particles. Heat from collisions and radioactive decay melts the interior, allowing heavier elements to sink and lighter ones to rise. This creates a layered structure over time, a core, a mantle, a crust. The earliest minds wouldn't need to intervene in these processes. They would simply understand how they play out and ensure that the starting conditions support a balanced result. Earth's formation fits this pattern. It grew from countless collisions in the early solar system. It developed a molten interior. It formed a dense core capable of creating a magnetic field. That magnetic field became essential for protecting the planet's atmosphere. A stable atmosphere became essential for maintaining the temperature range that allows liquid water. Liquid water became essential for the chemistry that eventually led to life. Each step depended on the previous one, and each step required conditions that could be predicted if someone knew enough about how planets evolve. If the earliest minds were guiding this process, they would not have needed to adjust every detail. They would only need to ensure that the ingredients were present in the right proportions. Iron for the core, silicon and oxygen for the crust. Water-bearing minerals scattered throughout the disk. Carbon compounds distributed in ways that allow them to be incorporated into the growing planet. All of these ingredients came from earlier stars. The earliest minds would have watched those stars form and die. They might have known exactly which stars produced the materials suitable for stable planets, and they could have guided the distribution of those materials into regions where new systems would later form. The process of planet formation is full of uncertainty when viewed from a human perspective, but uncertainty decreases when you observe millions of examples over billions of years. Patterns emerge, rules become visible, and with enough knowledge, guidance becomes possible. The earliest minds might have been able to predict which collisions would lead to stable growth and which would disrupt the system. They might have adjusted conditions to reduce destructive outcomes. They might have encouraged patterns that lead to long-lasting planets. Once a planet grows large enough, it begins to shape its own environment. Its gravity influences nearby bodies. Its heat influences the stability of the disk around it. its rotation affects how material collects. At this stage, the earliest minds might have stepped back, allowing the planet to continue developing naturally. They would not need to intervene constantly. They would simply ensure that the conditions continue to support long-term stability. In Earth's case, one of the most significant events in its early history was the formation of the Moon. According to scientific understanding, a large object collided with the early Earth, and the debris from that collision eventually formed the Moon. The Moon then played a major role in stabilizing Earth's tilt and regulating tides. Without it, Earth's climate might have been less stable. If the earliest minds had been guiding Earth's formation, they would have recognized the importance of such a stabilizing feature. They might not have caused the collision directly, but they could have allowed conditions that made such an outcome more likely. The presence of large bodies in similar orbits, the distribution of material in the disk, and the timing of impacts could all be influenced subtly without any drastic intervention. The earliest minds would have known that stability over billions of years requires not just a planet, but a balanced system. The presence of Jupiter in the solar system, for example, helps reduce the number of dangerous impacts on Earth. Jupiter's gravity pulls in comets and asteroids that might otherwise strike the inner planets. If the earliest minds understood this, they might have encouraged the formation of a large planet in the outer zone. Again, not by assembling it directly, but by guiding the distribution of matter so that a giant planet could form naturally in a stable orbit. Once Earth existed as a stable planet, its surface would still be hostile for a long time. Molten rock, intense volcanic activity, heavy impacts from leftover debris. The earliest minds might not have needed to influence this stage. They might simply have waited for the planet to cool, for the crust to solidify, for the first oceans to form through outgassing and impacts from water-bearing bodies. They would understand that cooling takes time, that water cycles stabilize temperature, that early atmospheres change through geological activity. None of these processes would surprise them. The idea of carving a planet from cosmic dust does not require imagining beings with tools or machines. It requires imagining minds that understand how natural processes behave and how small adjustments can influence long-term outcomes. They would not be sculptors in the human sense. They would be guides, shaping the environment in ways that allow planets to develop with the properties they want. A stable orbit, a protective magnetic field, a tilted axis, liquid water, active geology, long-term chemical cycles. These features are not common, but they are achievable. Earth has them, other planets do not. Some have magnetic fields but no stable atmosphere. Some have water but no solid surface. Some have stable orbits but no internal heat. Each missing feature changes the planet's potential. If a civilization wanted planets capable of supporting complexity, they would aim for worlds that balance these factors. Earth fits that pattern. The earliest minds might not have known what would grow on Earth. They didn't need to know. They only needed to create the conditions where complexity could increase over time. That's how systems evolve. You create a stable environment, and complexity finds its own path. When humans build something, they expect immediate results. But the earliest minds might have worked on timescales too large for immediate outcomes. They might have shaped environments knowing that the results would emerge millions or billions of years later. That kind of patience would be built into their nature. Their sense of stability would not be tied to a single moment. It would be tied to long-term balances. Once Earth developed a stable surface and oceans, chemical reactions became possible. These reactions eventually led to the first forms of life. The earliest minds might not have participated in these reactions. They might not have altered the chemistry directly. They might have simply ensured that the environment was stable enough for these reactions to continue over time. A planet with constantly changing conditions could not support long-term chemical complexity. But Earth maintained its balance. Temperature, water cycles, geological cycles, and atmospheric composition shifted, but not so drastically that complexity was lost. These conditions are rare. They require a combination of features that don't often align by chance. If the earliest minds influenced Earth formation, they might have predicted these results, not in terms of species or ecosystems, but in terms of long-term complexity. They would recognize that a balanced planet leads to interesting outcomes, and interesting outcomes produce new patterns. These patterns contribute to the growth of intelligence. Intelligence contributes to the potential for a new generation of minds. This might have been part of their purpose, not to create beings like themselves, but to create environments where new forms of intelligence could emerge under different conditions. Thinking about Earth in this way doesn't require seeing the earliest minds as creators in the traditional sense. They would be part of the universe, not separate from it. Their influence would blend with natural processes. Over time, their contributions would become indistinguishable from the behavior of the cosmos itself. Earth would not feel artificial. It would feel natural because the natural processes are the foundation of its formation. What changes is the starting conditions, the guidance. The small adjustments applied early enough that the final results emerge naturally. A world shaped by cosmic dust doesn't need a sculptor. It needs someone who understands dust, gravity, energy, and time. Someone who has watched stars form, planets grow, and systems evolve long enough to predict outcomes before they happen. Someone who can carve not by touching, but by guiding conditions in ways that lead to stability. Once a planet reaches the point where its surface cools and its crust begins to settle, the environment becomes a canvas for chemical and geological processes that will shape everything that comes afterward. Earth, during its early stages, was not the calm place people picture when they imagine oceans and blue skies. It was a world of rising steam, heavy volcanic activity, and constant shifts in temperature. But beneath the surface of those conditions were opportunities. Water appeared in the form of vapour, dissolved minerals collected in newly forming basins, and the crust fractured in ways that created openings for cycles that would eventually stabilise the planet. If the earliest minds were guiding anything at this point, they would not have been moving molecules directly. They would have been working with the larger patterns that decide where water gathers, how temperature distributes, and how atmospheres form from the gases released by rock and impacts. Water is not rare in the universe. It forms from hydrogen and oxygen, two of the most abundant elements. But liquid water is rare because it requires specific temperature and pressure conditions. A planet must be the right distance from its star. Its atmosphere must hold heat without trapping too much. Its internal activity must release gases and keep the surface warm enough to prevent freezing. These factors rarely align perfectly, but Earth managed to hold all of them in place long enough for the first oceans to appear. If the earliest minds wanted a stable, long-term environment capable of supporting complex chemistry, encouraging the formation and preservation of oceans would have been a priority. Oceans regulate temperature, store heat, cycle nutrients, and provide environments where molecules can interact more frequently than they would in air or rock. The early Earth received water from two main sources. One was the minerals inside the planet itself, released through volcanic activity. The other was objects in the solar system that carried water-bearing compounds, including comets and certain types of asteroids. These impacts were not random events. They followed paths determined by the distribution of matter in the solar system. If the earliest minds had guided the formation of the solar system, they might have influenced how much of this water-bearing material reached the inner planets. They wouldn't need to direct individual objects. They would only need to influence the distribution of material in the early disk, which determines how many water-bearing bodies migrate inward and how many remain farther out. As water began to accumulate on Earth, it didn't immediately form deep oceans. It collected in basins created by the cooling crust, but the temperature was still high enough that much of it remained in vapor form. Over time, as the planet radiated heat and volcanic gases thickened the atmosphere, clouds condensed and rainfall became continuous. For thousands of years, rain poured across the surface, filling the deepest regions with water. The earliest minds, if they observed this stage, might have recognized that water would become the stabilizing force the planet needed. Oceans, moderate temperature. They absorb heat when the planet warms. They release it when the planet cools. This buffering effect would allow complex chemistry to persist without constant interruption from extreme conditions. The presence of water is not enough on its own. The chemistry within water must also be conducive to complexity. Water dissolves minerals from rock, creating mixtures that can participate in chemical reactions. Some reactions require heat, others require cooler conditions. Oceans provide both in different regions. Near volcanic vents, the temperature rises enough to drive reactions that would not occur on the surface. In shallower regions, sunlight influences reactions differently. This variety allows a range of molecular structures to form and interact. The earliest minds would not need to design these reactions. They would only need to appreciate that an ocean-covered world offers more opportunities for complexity than a dry one. As Earth's oceans grew, the atmosphere changed as well. The early atmosphere was not breathable for humans. It contained gases released by volcanic activity, including carbon dioxide, water vapor, methane, and sulfur compounds. These gases help trap heat, keeping the planet warm enough for water to remain liquid. Without this natural greenhouse effect, Earth might have frozen completely. The earliest minds would have understood that a certain balance of gases supports long-term stability. Too little atmospheric pressure and water boils away. Too much and heat becomes difficult to regulate. A balance is necessary. Earth managed to find that balance during its early development, and this balance continued to evolve as life eventually began to influence the composition of the atmosphere. If the earliest minds played a role in shaping this balance, they might have influenced volcanic activity indirectly by guiding the internal structure of the planet. A planet with an active interior produces gases consistently. That consistency supports a stable atmosphere. Earth's core generates heat through radioactive decay and residual energy from its formation. This heat drives convection in the mantle, which leads to volcanic activity and plate movement. Some planets cool too quickly and lose their internal activity. Others remain too hot and unstable. Earth found a midpoint that allowed long-term internal movement. The earliest minds, if they guided the distribution of heavy elements during Earth's formation, might have influenced this outcome. As the ocean stabilized and the atmosphere thickened, another important factor began to appear: sunlight interacting with water and minerals. Sunlight provides energy that drives certain reactions. On the early Earth, sunlight reached the surface through gaps in the clouds and through shallow waters. Deep regions remained dark but received energy from volcanic vents. These varied environments allowed molecules to form, break apart, and recombine in different ways. Over time, some of these reactions produced structures that could store information, replicate with variations, and interact with their surroundings in ways that increased their stability. The earliest minds would have recognized these developments not as life, but as increasing complexity. Complexity is predictable when the environment remains stable long enough. At the same time, the atmosphere continued to evolve. The early gases created a warm, thick environment, but as chemical processes in the oceans progressed, some compounds formed that could release oxygen slowly. This did not happen quickly. It took enormous spans of time for oxygen to accumulate in the atmosphere. Most of the early oxygen was absorbed by minerals in the oceans. Only after these minerals had been saturated could oxygen become a significant part of the air. When it did, it transformed the planet. Oxygen is a highly reactive gas. It enables energy-rich chemical reactions. It allows organisms to produce far more energy per reaction than they could in oxygen-poor environments. This transformation laid the foundation for future complexity on Earth. The earliest minds observing this might have seen the shift not as a sudden change, but as part of the planet's long-term evolution. They would understand that oxygen introduces new pathways for complexity. They wouldn't need to intervene directly in the chemistry. They would simply need to recognize that a planet with oceans and an evolving atmosphere offers opportunities for increasing complexity. Over time, these opportunities turn into long-term outcomes. But before oxygen became a major atmospheric component, the planet relied on other gases to maintain temperature. Carbon dioxide played a major role. Too much carbon dioxide would cause runaway heating. Too little would allow the planet to freeze. Earth's geological cycles helped regulate this balance. Weathering of rocks removes carbon dioxide from the atmosphere gradually. Volcanic activity adds it back. These opposing processes maintain long-term stability. If the earliest minds had knowledge of these cycles, they might have chosen to guide Earth's formation in a way that favoured active geology. A planet without plate movement would not recycle carbon dioxide effectively. Over time, its atmosphere would become unstable, but Earth maintained active cycles that kept its climate within a range suitable for complexity. The formation of oceans and atmosphere is only part of the story. The next part involves the conditions that allow these systems to work together over long periods. The earliest minds might have understood how important it was for a planet to keep liquid water over billions of years. Many planets start with water but lose it over time due to solar radiation or a lack of magnetic protection. Earth avoided this because of its magnetic field, produced by the movement of molten iron in its core. Without this field, charged particles from the sun would strip the atmosphere over time, causing the oceans to evaporate. The earliest minds might have recognized the importance of a strong magnetic field long before humans understood its role. If they shaped Earth's formation by guiding the distribution of heavy elements, they may have ensured that Earth developed a dense core capable of supporting a magnetic field. As Earth continued to cool and stabilize, the oceans became the primary environment for chemical development. Over time, molecules became more complex. Some molecules formed structures that could respond to environmental changes. Some formed membranes that allowed internal conditions to differ from external ones. These membranes became the first boundaries that allowed complexity to increase in controlled environments. The earliest minds might not have interacted with these developments. They might have simply watched as the planet they guided created the conditions necessary for complexity to grow. The appearance of early life did not involve recognizable organisms. It involved chemical systems capable of replication with variation. Variation allowed certain structures to become more stable than others. Stability favored replication. Replication created cycles. These cycles eventually produced diversity. Over long periods, these simple replicating systems became more complex, forming the basis for cells. The earliest minds would have understood that once such cycles begin, complexity becomes almost inevitable as long as the environment remains stable. As these early organisms grew in number, they began to influence the atmosphere. Some produced oxygen as a byproduct of their energy processes. This oxygen reacted with minerals in the ocean, slowly filling them. Only after these minerals were saturated could oxygen accumulate in the air. This accumulation changed the planet drastically. Many early life forms could not tolerate oxygen and declined. Others adapted. Over time, the balance shifted toward oxygen-dependent processes because they produce more energy. The earliest minds would have recognized this shift as another stage in the planet's development. More energy availability means more complexity. More complexity means more potential pathways for structures that store and use information. Information storage is a foundation for intelligence. The earliest minds would have understood this progression long before complex life emerged. When oxygen became a major part of the atmosphere, it changed not only life, but also the surface of the planet. Oxygen allowed for the formation of the ozone layer, which protects the surface from harmful ultraviolet radiation. With this protection, life could expand into new environments. This expansion increased diversity. Diversity increases resilience. Resilience allows complexity to persist even when conditions change. The earliest minds might have predicted these developments in broad terms. They would not have known what specific structures would emerge, but they would have understood that a planet with oceans, an evolving atmosphere, and long-term stability offers many routes toward intelligence. The processes that shaped Earth over billions of years are intricate, but they follow rules. The earliest minds might have learned those rules through experience. Their knowledge would have allowed them to guide the formation of worlds in ways that encourage long-term complexity. If they influenced Earth, their actions were not direct manipulations of oceans or air, but gentle adjustments that allowed these systems to develop naturally. Oceans and atmosphere work together as regulators. Oceans store heat, atmosphere distributes it. Geological cycles recycle gases. Magnetic fields protect the whole system. All of these features must align for a world to support complexity for billions of years. Earth achieved that alignment. A world shaped by guidance rather than construction would not appear artificial. It would follow natural processes exactly, because those processes are the most efficient way to produce stable outcomes. If the earliest minds shaped anything, they shaped conditions. Conditions gave rise to oceans. Oceans gave rise to breath. Breath in the chemical sense before breath in the biological sense. Eventually, breath in the biological sense became possible because the foundation had already been laid. As Earth's oceans and atmosphere settled into long-term patterns, the planet was still far from the balanced environment people know today. Water moderated temperature, but the surface continued to change constantly. Volcanoes reshaped coastlines, impacts rearranged basins. The crust shifted as the interior circulated heat. None of these processes were stable yet. But beneath this constant movement were the beginnings of something that would later define Earth as a place capable of sustaining a wide range of environments. This next stage involved more than water and air. It involved the land itself rising and falling, reshaping how heat moves across the surface, how winds form, how moisture travels, and how life eventually spreads. If the earliest minds were watching this, they would have recognized it as another step in the gradual progression toward long-term complexity. The presence of continents is not guaranteed on any planet. Continents require specific conditions inside the planet. The crust must contain minerals that can become buoyant enough to rise above the denser oceanic crust. This process depends on the types of rocks formed in the early mantle, the temperature of the interior, and the movement of plates driven by convection. Earth's continents formed because its interior maintained just the right balance of heat and composition. Too much heat and the crust becomes too thin to rise. Too little heat and the crust becomes too rigid to move. The earliest minds, if they had influenced Earth's formation, would have understood how important internal temperature is for long-term stability. Continents break the ocean into separate regions. They create coastlines where cycles of evaporation and rainfall intensify. They produce mountain ranges where air cools and water condenses. These features are not random. They shape weather, climate, and eventually ecosystems. As the continents formed, they did not remain fixed. They drifted slowly across the surface. This drifting is the result of plate movement, driven by heat rising from the planet's interior. Plate movement recycles rock, exposing new minerals and pulling old ones into the mantle. This cycle influences atmospheric gases. It exposes fresh rock that reacts with carbon dioxide. It releases gases through volcanic vents. It shapes coastlines and creates environments with varied temperatures and rainfall. A planet without moving plates lacks this variety. It becomes geologically quiet. Without geological variety, oceans may still exist, but the processes that regulate atmospheric composition weaken. That kind of planet can become stable, but it doesn't support the same long-term complexity that Earth does. If the earliest minds wanted a planet where complexity could continue to increase over billions of years, they would have recognized the importance of active geology, not just volcanoes or earthquakes, but the slow, steady drift of continents that reshapes environments over time. Plate movement creates collisions between crustal sections. These collisions push rock upward to form mountains. Mountains are more than landforms. They influence temperature, rainfall, erosion, and the movement of water across the landscape. They create shadows that shape climate patterns. They divide ecosystems and encourage different forms of life to emerge in different regions. A planet with mountains has a level of environmental diversity that increases the potential for complex structures to develop. When mountains form, they change how air moves. Warm air rises along slopes, cools at higher altitudes, and condenses into clouds. These clouds release rain on one side of the mountain. The other side becomes dry because the air has already lost its moisture. This separation creates distinct climate zones. Over time, these zones shape the types of plants and animals that can thrive there. Even before life reached the land, mountains shaped weather patterns that influenced the chemistry of the atmosphere and the flow of minerals into the ocean. These flows provided nutrients for early marine ecosystems. In this way, mountains are part of a larger system that connects land, air, and water. The earliest minds observing Earth's development might have seen mountains not as structures, but as part of the planet's ability to regulate itself. Mountains erode through wind and rain, carrying minerals back to the sea. These minerals interact with ocean chemistry, influencing how much carbon dioxide is absorbed from the atmosphere. This process helps maintain the balance necessary for keeping the planet warm but not too warm. It is a slow cycle. It requires millions of years to see the effects clearly. But for beings accustomed to long time scales, these patterns would be familiar. Mountains also influence rivers. Rivers carve landscapes, transport nutrients, and create environments where sediment can accumulate. These environments become shallow regions filled with sunlight, minerals, and organic matter. On early Earth, such places provided ideal conditions for more complex organisms to develop. Sunlight could reach the water, nutrients arrived steadily, temperature fluctuated gently. These features allowed chemical systems to stabilize and diversify. Without mountains driving water cycles, these environments might have been limited or absent. As Earth's continents continued drifting, mountains formed, eroded, and formed again. Over time, the distribution of land changed the shape of ocean currents. Ocean currents transport heat across the planet. They move warm water from the equator toward the poles and cold water from the poles toward the equator. This movement creates a global climate that is neither uniform nor chaotic. It becomes patterned. Regions develop predictable temperatures and seasons. Predictability allows complexity to flourish because organisms can adapt to repeating conditions. The earliest minds would have recognized that stability does not mean uniformity. It means patterns that repeat enough to allow long-term adaptation. Earth's atmosphere, shaped by oceans and geology, began to take a more stable form as continents settled into larger structures. Weather systems emerged from interactions between sunlight, land shapes, and the rotation of the planet. Winds formed when warm air rose and cooler air flowed in to replace it. The rotation of the planet caused these winds to curve, producing global wind patterns. These patterns distribute moisture. They shape storms. They influence how quickly heat escapes into space. All of these processes would have been predictable to anyone who had observed similar systems on other worlds. If the earliest minds had guided the formation of Earth, they would have understood that weather patterns influence more than climate. They influence chemistry. Lightning provides energy that can drive chemical reactions. Rain dissolves minerals and transports them. Storms mix layers of the atmosphere. The earliest atmosphere was thick and warm, but as the planet cooled and oxygen increased, weather systems changed. They became more complex, creating pressures and temperatures that varied across the surface. These variations created new opportunities for molecules to interact in ways that led to more diverse forms of life. Landscapes created by mountains and erosion also offered protected environments. Valleys, caves, and shallow pools provided places where temperature remained more stable. These sheltered environments could support chemical systems sensitive to extreme changes. Over time, some early organisms moved into these areas, taking advantage of the stability. The earliest minds might not have known which environments would support life best, but they would have recognized the value of variety. Variety increases the number of possible outcomes. The more outcomes, the greater the chance that some will lead to more complex forms. As life expanded across the planet, the architecture of the land continued to influence its development. Mountains create barriers that separate populations. Separation allows different groups to follow different paths. Over long periods, those paths lead to diversity. Diversity increases the planet's ability to adapt to changing conditions. Some environments will become too cold or too dry, others will remain stable. A planet with varied landscapes provides more options for resilience. Weather systems, shaped by mountains and oceans, determine how energy is distributed. Without storms, heat would accumulate in some regions and dissipate too quickly in others. Without wind, moisture would remain in narrow bands. Without currents, temperatures would be extreme. The earliest minds might have seen weather not as random, but as a vital component of stability. Predictable storms, reliable winds, and stable currents create a planet where life can adapt over time. Life on Earth required not just water and air, but a surface that changed slowly enough for adaptation to keep pace. Continents drifted, but not too quickly. Mountains rose, but not instantly. Weather shifted, but not in ways that prevented long-term patterns. The earliest minds could have recognized that a planet with these characteristics offers more potential than one where conditions change too quickly or not at all. As the first simple organisms began to process sunlight, release oxygen, and shape the chemistry of the oceans, the architecture of the land became increasingly important. Nutrients washed down from mountains fed these organisms. Sediment created shallow regions where sunlight penetrated the water. Over time, more complex structures formed. These structures eventually led to organisms capable of moving onto land. The transition from ocean to land required environments with intermediate conditions. Coastal areas provided these. Changing tides created wet and dry cycles. These cycles influenced early organisms, challenging them to survive temporary exposure to air. The earliest minds would have seen that such environments create opportunities for new forms to emerge, not because they intended specific outcomes, but because they understood that transitional environments encourage adaptation. Once life reached the land, the architecture of Earth shaped its development even more directly. Mountains influenced rainfall patterns that determined where plants could grow. Plants stabilized soil, allowing more complex ecosystems to form. Weather patterns shaped migration paths. Temperature variations created different habitats. All of these features contributed to the increasing complexity of life. The architecture of Earth is a combination of geological movement, erosion, and climate. These processes interact in ways that create long-term patterns. For the earliest minds, if they had a purpose connected to complexity, guiding the formation of mountains, continents, and weather patterns would have been a practical approach. They wouldn't need to control every detail. They would simply need to shape the broad environment and allow natural processes to do the rest. Earth's mountains rose and eroded countless times. Each cycle provided new minerals, new coastlines, and new environments. These changes allowed life to expand into new regions while maintaining overall stability. Stability and change coexisted. Too much change would disrupt life. Too little change would limit opportunities. Earth found a balance between the two. This balance created the architecture necessary for complexity to flourish. Weather systems became more organized as the atmosphere evolved. Rainfall patterns became consistent enough to support forests. Forests influenced carbon cycles, stabilizing the climate. Wind patterns carried seeds and shaped plant distribution. Temperature gradients created migration patterns for animals. These interactions contributed to the emergence of ecosystems that supported increasingly complex forms. From a long-term perspective, Earth appears to be a system that regulates itself. Geological cycles maintain atmospheric balance. Weather patterns distribute heat. Mountains shape environments. Oceans moderate temperature. Life influences chemistry. This regulation is not perfect. The planet undergoes shifts, cycles, and disruptions. but the overall pattern tends towards stability over long periods. The earliest minds might have recognized that such a system, once established, could continue to support complexity without further intervention. As life diversified, the architecture of Earth played a role in shaping intelligence. Forests, plains, mountains, and coastlines required different adaptations. Organisms that navigated these environments developed new behaviors. Some learned to use tools, some developed complex communication, some formed social structures. Intelligence emerged not as a singular event, but as a gradual process influenced by the variety of environments on the planet. If the earliest minds intended to create conditions where intelligence might arise, they would not need to plan specific outcomes. They would only need to create variety, stability, and long-term cycles. Earth provided all three. The architecture of the planet offered countless pathways for life to adapt, diversify, and grow in complexity. As life spread across Earth and adapted to the variety of environments shaped by oceans, mountains, weather, and shifting continents, something else began forming quietly within living systems. It wasn't a structure like a bone or a shell. It wasn't a behavior like migration or hunting. It was a pattern that existed inside almost every organism, from the simplest single-celled forms to the complex animals that eventually walked on land. This pattern is something modern science calls a circadian rhythm, but a simpler way to think about it is as a biological clock, a system that regulates when organisms wake, rest, eat, reproduce, repair, and adapt. This clock exists in creatures that have no awareness of time. It exists in organisms that cannot sense light in any conscious way. It is built into the chemistry that keeps life functioning. If the earliest minds shaped the conditions that allowed life to form, they might not have designed this clock intentionally, but they would have understood the importance of rhythms long before biological systems existed. The universe is full of cycles. Stars brighten and dim, planets rotate, moons orbit, magnetic fields pulse, radiation waves shift. These cycles influence energy flows. Energy flows influence matter. Matter influences chemistry. Chemistry influences life. A clock is not an invention inside a living system. It is an adaptation to the cycles that existed long before life appeared. When Earth finished cooling enough for stable oceans and a consistent atmosphere, the sun became the most reliable source of energy. Its light reached the surface in daily intervals due to Earth's rotation. Day brought warmth and energy. Night brought cooler temperatures and darkness. These patterns were predictable. They repeated consistently enough that early chemical systems experienced cycles without being aware of them. Temperature fluctuated in regular intervals. Light intensity changed in regular intervals. Some reactions occurred more efficiently in warmth. Others occurred in cooler conditions. Over time, chemical systems that could anticipate or respond to these cycles developed advantages. The earliest minds observing this might have recognized that organisms with built-in timing could function more efficiently. A system that can anticipate an environmental change does not need to react suddenly. It can prepare. Preparation saves energy. Energy efficiency increases stability. Stability increases survival. Over millions of years, this principle could lead to a biological clock even without direct intervention. But if the earliest minds understood the value of predictable cycles, they might have guided Earth's rotation indirectly by influencing how the early planet accumulated angular momentum. A stable rotation period creates a predictable day length. Predictable day length encourages the development of biological rhythms. When early life began developing modules for energy production, the availability of sunlight became a central factor. Organisms that use sunlight needed to manage their internal processes based on its presence or absence. Light-sensitive molecules formed, not because organisms sought to detect light, but because light provided energy that changed molecular structures. These structural changes created opportunities for reactions that wouldn't happen otherwise. Over countless cycles of light and dark, molecules that responded to light began influencing other reactions. Eventually, this interconnected system became a primitive version of a biological clock. It wasn't conscious, it wasn't precise, but it created patterns of activity that matched the environment. The earliest minds might not have interfered with these developments, but they would have understood them. They would recognize that timing systems within organisms create advantages that allow complexity to grow. When life can schedule processes instead of reacting constantly, it can allocate energy to growth, adaptation, and resilience. A biological clock is not a luxury. It's part of the framework that supports long-term survival. As organisms became more complex, the internal clock became more refined. Chemical feedback loops formed. Proteins rose and fell in concentration based on timed interactions. These interactions created repeating cycles within cells. Over time, these cycles coordinated with external cues like light and temperature. In multicellular organisms, coordination extended across tissues. Some parts of the body became specialized in detecting light. Others became specialized in managing internal timing. This specialization created a system where the entire organism could follow a unified rhythm. This rhythm influenced sleep, feeding, movement, growth, and repair. It influenced hormone release, temperature regulation, and cellular maintenance. All of these functions benefit from timing. Doing everything at once would be chaotic. Spacing tasks across cycles reduces stress on the system. The earliest minds, had they been able to perceive these developments, would see that the biological clock is a natural extension of the environment they helped shape. But the story doesn't stop at daily rhythms. Life also adapted to longer cycles. Seasonal changes driven by Earth's tilt created yearly fluctuations in light and temperature. Many organisms learned to track these cycles. Some reproduced at times when food was abundant. Others migrated when temperatures shifted. Plants coordinated flowering with temperature changes. These seasonal rhythms became part of the biological architecture. If the earliest minds guided the tilt of Earth's axis, they might have known that slight variations over time could create environments with consistent seasonal cycles. Seasonal cycles encourage diversity. Diversity encourages complexity. There are even longer cycles that influence life. Lunar cycles. The moon's gravitational pull affects tides. Tides influence coastal ecosystems. Early organisms near shorelines experienced cycles of rising and falling water. These cycles affected feeding opportunities, nutrient flows, and environmental conditions. Some organisms adapted by synchronizing reproduction with the tides. Over time, these biological cycles became as embedded as daily rhythms. They don't require consciousness. They arise from repeated environmental patterns. The earliest minds, if they were aware of Earth's development, might have recognized the value of these lunar cycles. The moon's presence stabilizes Earth's tilt and slows its rotation gradually. This slowing changed day length over millions of years, influencing how biological clocks evolved. A planet without a large moon would have different cycles. Life might still emerge, but its relationship to environmental rhythms would differ. The biological clock also responds to internal cues unrelated to external cycles. Organisms track hunger, fatigue, damage, and reproduction internally. These internal signals often align with environmental patterns, but they do not depend on them entirely. A well-functioning biological system can maintain its internal rhythm even when external cues change temporarily. That internal rhythm is what keeps organisms functioning when conditions shift. This resilience is part of what allowed life to spread across varied environments. The earliest minds might have understood that internal timing systems help life adapt to unpredictable events. A storm can hide the sun. A volcano can alter temperature. A long winter can delay growth. But organisms with internal clocks maintain consistent patterns even through disruptions. This consistency increases stability, allowing complexity to persist even when conditions change unexpectedly. As life evolved further, Biological clocks became more tightly integrated with behaviour. Animals began to structure their activity around the time of day. Some became active during daylight, others became active at night. These distinctions reduced competition and allowed species to specialise. Specialisation increases complexity in ecosystems. Complexity leads to new interactions. New interactions create new pathways for evolution. The earliest minds would understand that timing is not just an internal mechanism, it shapes entire ecosystems. Predators learn when prey are active. Plants release pollen when pollinators are active. Water cycles and weather patterns influence when organisms feed, reproduce, or migrate. These relationships form networks. Network supports stability. Stability supports long-term complexity. Inside humans, this biological clock remains deeply embedded. It influences sleep cycles, hormone levels, digestion, attention, and mood. Humans often think of time as something measured by clocks on walls or devices. But the internal clock continues operating regardless of external measurement. It is synchronized by light and temperature, but it does not depend on artificial timekeeping. It is part of the inherited structure shared with all other living beings on Earth. This internal timing system is a reminder that life evolved in a world shaped by cycles. Cycles created by the rotation of a planet, the orbit around a star, the pull of a moon, the movement of continents, the tilt of an axis. These cycles existed long before complex life. They influenced the earliest chemical reactions that led to life. They guided the patterns that shaped ecosystems. If the earliest minds had any role in shaping Earth, one of the most significant contributions they could have made was ensuring that these cycles remained stable. The idea that life carries an imprint of cosmic cycles is not metaphorical, it is biological. Organisms evolved internal clocks because the environment offered predictable cycles worth adapting to. Those cycles come from planetary mechanics shaped during formation. And if the earliest minds influenced Earth's formation, then they indirectly influenced the biological clock inside every organism alive today. The biological clock also interacts with memory and behaviour. Humans remember events partly based on time of day. They feel alert at certain times and tired at others. Their bodies repair tissues more efficiently at specific periods. Hormones rise and fall in patterns that repeat daily. These patterns are not conscious choices. They are inherited structures shaped by evolutionary history, and evolutionary history is shaped by environmental cycles. The earliest minds would not have needed to design neurons or hormones. They would simply need to ensure that Earth offered predictable cycles. Life would take care of the rest through adaptation. Over long periods, internal clocks became more sophisticated. They extended beyond simple energy management systems. They became integrated with social behaviour. Animals coordinate their activity with the group. They migrate collectively. They raise offspring during seasons with optimal resources. Internal timing systems help coordinate these behaviours so that groups function more effectively. Some organisms evolved clocks that track much longer cycles. Certain species track multi-year cycles of climate. Some track cycles of ocean currents. Others track cycles of food availability or rainfall. These long cycles shape how species interact with the planet's rhythms. Entire ecosystems depend on these patterns. If the earliest minds observed Earth's development, they would see that biological clocks create stability, even when external conditions shift. This stability supports the long-term growth of complexity. Inside humans, the biological clock functions through a small group of cells deep in the brain, responding to light that enters the eyes. But the clock does not reside only in the brain. Nearly every cell has its own internal rhythm. These rhythms coordinate through signals that flow across the body. The entire system works because it is synchronized with environmental cycles. Humans can override these signals temporarily with artificial light or irregular schedules, but the internal clock continues to operate. It adapts but never stops. This persistence reflects the deep connection between life and the cycles shaped by the planet. A biological clock is not just a feature of modern organisms, It is a legacy of the environment in which life evolved. If Earth had irregular rotation or unpredictable cycles of light, biological clocks might not have developed in the same way. Timing systems would be less consistent, and complexity could be limited by constant environmental uncertainty. The earliest minds would understand that predictable cycles create opportunities for life to grow in complexity. They would recognize that stability across billions of years allows these patterns to remain anchored in the biology of organisms. They might not have intended to create a clock inside living beings, but by influencing the environment, they created the conditions that led to its development. The biological clock not only helps organisms survive day to day, but also links them across generations. Every living being inherits rhythms that originated in early chemical systems responding to cycles. These rhythms persist even as species evolve, diversify, and change. They remain as a shared structure connecting all life to the environment that shaped it. As life continued to expand across Earth and internal rhythms became more refined, the planet accumulated layer upon layer of biological, geological, and atmospheric complexity. Each layer built upon the ones before it, creating a world where patterns from the earlier stages of Earth's formation remained embedded in systems that people see today. These patterns aren't usually noticed. They sit quietly beneath the more obvious processes of weather, growth, behavior, and change. But if someone were to look carefully, with an understanding that patterns can reflect influence even when intentions are not clear, they might begin to notice hints of structure that appear too consistent to be the result of randomness alone. These hints are not artifacts or physical markers. They are signs in the sense that they reflect decisions made during times when the planet was still shaping itself, before life had eyes or awareness, but not before intelligence had the ability to guide the conditions from which life developed. To understand how such signs might exist, it helps to consider how influence works in systems that operate over long timescales. A single change applied early can alter outcomes billions of years later, not because the change was large, but because the system amplifies differences as it evolves. This is true in biology, geology, and even weather. In the early universe, small differences in density shaped galaxy formation. In early life, small differences in chemical structure shaped evolution. In early Earth's formation, small adjustments could have influenced the distribution of continents, the composition of the atmosphere, or the patterns of seasons. Influence doesn't need to reveal itself in obvious ways. It can remain invisible until someone understands the underlying process well enough to detect inconsistencies or patterns that stand out. One of the places where fingerprints of guidance might appear is in the repeated alignment of conditions that support long-term stability. Earth contains patterns that seem coincidental when considered individually, but when viewed together, they form a network of conditions that maintain a delicate balance. The size of the planet determines its gravity. That gravity holds an atmosphere thick enough to support liquid water. The mass of the core creates a magnetic field strong enough to protect that atmosphere. The distance from the sun provides a temperature range suited for oceans. The tilt of the axis creates seasons without extreme swings. The presence of the moon stabilizes that tilt. The rotation speed generates cycles that life can adapt to. Each of these factors has natural explanations, but natural explanations do not exclude the possibility of influence. Natural processes can be guided. They can be shaped early enough that the results appear as coincidences rather than constructions. If the earliest minds understood how to influence these processes, their fingerprints might be found in the consistency of these patterns, rather than in any single element. Another quiet fingerprint might appear in the relationship between Earth's atmosphere and its long-term stability. The atmosphere is composed of gases released through geological activity. Volcanoes release carbon dioxide. Rocks absorb it over time. Plants release oxygen. Ocean chemistry balances nutrients. These systems interact in ways that regulate the climate. The balance is not perfect, but it is stable enough to allow complexity to grow. A slight shift in volcanic activity, rock composition, or ocean circulation could make the planet uninhabitable. But Earth's systems have remained within a stable range for billions of years despite meteor impacts, ice ages, volcanic eruptions, and shifts in the sun's brightness. This resilience may be natural, but it could also be an indication that the planet's starting conditions were set in a way that encourages long-term stability. Signs of guidance don't need to appear in obvious structures. They can appear in the consistency of environmental regulation. A planet that regulates itself without conscious intervention resembles a system designed to maintain balanced conditions. If early minds guided the distribution of heavy elements during Earth's formation, they could have influenced the strength of the magnetic field. A strong magnetic field helps maintain the atmosphere, which stabilizes climate. If they guided the timing of the moon's formation, they could have stabilized Earth's tilt. If they influenced the distribution of matter in the early solar system, they could have created a configuration where large planets protect inner ones from frequent impacts. These possibilities are not claims. They are examples of how influence could manifest as signs without ever producing direct evidence. Fingerprints in this sense are patterns that show alignment with expectations formed by beings who understood the importance of stability. Stability supports complexity. Complexity supports intelligence. The earliest minds, if they valued complexity, would guide systems towards stability, regardless of whether they expected creatures like humans to emerge. Beyond planetary systems, there are fingerprints that might appear in biological patterns. The genetic code used by all life on Earth is nearly universal. Differences exist, but the core structure is consistent across bacteria, plants, fungi, and animals. This consistency suggests a shared origin, which aligns with scientific understanding. But if early minds influenced the environment that shaped the earliest chemical cycles, they might have guided conditions that made this particular code more stable or more likely to succeed. The code balances redundancy with efficiency. Redundancy prevents errors from causing catastrophic failures. Efficiency allows rapid adaptation. These features are beneficial for long-term complexity. If conditions encouraged a code with these properties, the result might resemble a symbol of influence by designers who understood the importance of reliable information systems. The structure of DNA also reflects patterns that support long-term stability. Its double-stranded form provides backup information. Its ability to replicate with variation supports evolution. Its chemical composition allows for stability across a range of temperatures and conditions. These features emerge naturally from chemistry, but chemistry is shaped by environmental conditions. If the earliest minds influenced those conditions, their fingerprints might appear indirectly in the chemical pathways that became dominant. Another area where subtle signs might exist is in the relationships between life and geology. The cycling of carbon, nitrogen, and oxygen depends on interactions between the atmosphere, oceans, and land. These cycles operate on long timescales and remain stable despite disturbances. The balance of these cycles supports climate regulation and nutrient distribution. A planet without this balance could support life briefly, but would struggle to maintain complexity over time. The cycles on Earth are unusually effective at maintaining long-term stability. They might reflect natural processes, but they could also represent conditions shaped by beings who understood that long-term complexity requires consistent regulation. People often imagine that signs of design would appear as objects or markings, but on a planetary scale, influence would appear in patterns rather than artifacts. Fingerprints could be structural, they could be environmental, they could be statistical. For example, the distribution of elements in Earth's crust is suitable for supporting life. Some elements essential to biology are abundant within accessible layers rather than buried deep below the surface. Others that are harmful appear in lower concentrations or in forms that do not easily enter biological systems. These distributions can arise naturally from differentiation processes, but they also align with what would be expected if someone wanted to create a planet where chemical complexity had room to grow. Even the timing of events on Earth reveals patterns that could reflect influence. Life appeared relatively early in Earth's history, once conditions stabilized enough for complex chemistry. But it did not accelerate too quickly. The pace allowed systems to develop gradually without becoming unstable. Oxygen increased slowly enough to avoid immediate global disruption, but quickly enough to create opportunities for new energy pathways. Mass extinctions removed some forms of life but opened the door for others. These patterns can be explained through natural processes, but they also align with what might happen if early conditions were set to encourage balanced progression, rather than chaotic swings. Another subtle sign might appear in the fact that Earth's complexity increased steadily over time, but not in a single direction. Progress was not linear. It involved branches, setbacks, and recoveries. This non-linear progression increases resilience. Systems that rely on a single path are fragile. Systems that explore many paths adapt more effectively. If the earliest minds understood complexity deeply, they might have guided Earth's conditions to support non-linear development. This type of development leaves no direct mark, but the structure of life's evolution reflects it. People often focus on the question of whether life was created, but guidance is different from creation. Guidance leaves fewer obvious traces. It does not require altering natural laws or creating new materials. It requires understanding how natural processes respond to initial conditions. The earliest minds might have used that understanding to shape environments in ways that increase the likelihood of outcomes they valued. These outcomes do not need to be specific. They can be broad, such as increased complexity, stability, or opportunities for intelligence. One of the most intriguing fingerprints might be found in the alignment between planetary cycles and biological cycles. Life adapts to day-night cycles, seasonal cycles, and tidal cycles. These cycles depend on Earth's rotation, orbit, tilt, and moon. If early minds influenced any of these factors, their influence would appear in biological rhythms that persist across all forms of life. These rhythms are not symbols in the traditional sense, but they function like signatures. They reflect the connection between life and the environment that shaped it. They demonstrate that organisms carry an imprint of planetary history within their structure. Some signs might appear in the behavior of ecosystems. Ecosystems rely on balance between species. Predators regulate populations of prey. Plants regulate atmospheric gases. Decomposers recycle nutrients. These relationships form networks that support long-term stability. Networks that collapse easily would limit complexity. But Earth's ecosystems have recovered from countless disruptions. This resilience might be natural, but it also resembles the behavior of systems designed to maintain balance. Not consciously designed, but shaped in ways that encourage balance through structural reinforcement. The earliest minds, if they ever influenced Earth, would not need to leave symbols carved into rock. Their influence would be woven into the structure of systems that survive long enough to develop intelligence. The quiet fingerprints of designers would be patterns that maintain stability, encourage complexity, and increase the likelihood that intelligence emerges. These fingerprints would be easy to overlook because they blend with natural processes. They do not reveal themselves through discontinuity. They reveal themselves through consistency that exceeds what randomness alone would predict. Signs can also appear in the way intelligence interacts with its environment. Humans, like all organisms, carry internal clocks shaped by environmental cycles. They rely on nutrients distributed by geological processes. They breathe gases balanced by biological and atmospheric systems. They think using energy produced by oxygen-based reactions. Every aspect of human existence depends on systems established long before humans appeared. These dependencies form a map of connections that trace back to the earlier stages of Earth's formation. If early minds shaped those conditions, humans carry the results of that guidance in every part of their biology. The absence of obvious evidence does not rule out influence. Subtle influence is more effective at guiding long-term outcomes without disrupting natural processes. If the earliest minds valued stability and complexity, their signs would appear in the foundations of the planet rather than in additions to it. Their fingerprints would be visible in alignments that persist across billions of years, alignments that support life not just briefly, but across transformations, disruptions, and evolutionary leaps. If the patterns shaping Earth's formation, its cycles, its biological clocks, and its long-term stability reflect even subtle guidance, then the next question is unavoidable. It isn't about how Earth might have been influenced, or what the earliest minds may have done. It shifts toward the beings who eventually emerged in those conditions, individuals who walk across landscapes shaped by geological cycles, individuals who rely on oxygen produced by ancient organisms, individuals who live by internal clocks tuned to planetary rhythms, individuals who build tools, explore ideas, ask questions, and wonder about their place in the universe. If Earth is engineered, even in the sense of early guidance rather than intentional construction, what does that imply about the creatures who evolved on it? This question isn't about hierarchy. It isn't about purpose. It isn't about suggesting that humans are products of a plan or that humanity is positioned at the centre of something. It is about understanding how environment influences development. Every organism reflects its environment. The structures inside cells mirror the chemistry of the ocean. The shape of limbs reflects the demands of land and gravity. The behaviour of animals reflects the conditions that favour survival. Humans are no different. They evolved within a world shaped by patterns that existed long before them. If some of those patterns were guided, then humans carry the results of that guidance in every part of their being. When thinking about what humans are in this context, the starting point is biological. Humans are organisms shaped by evolution. Their traits emerge through countless generations influenced by environmental pressures. Vision developed in environments where light was important. Hands developed in environments where manipulation provided an advantage. The brain developed in environments where flexibility helped survival. None of these developments require intention. They arise naturally. But if the earliest minds influence the environment that produced these pressures, then evolutionary outcomes reflect that influence indirectly. This doesn't make humans creations in the traditional sense. It makes them products of conditions that might themselves be the result of earlier intelligence. In that case, humans are not designed beings. They are emergent beings shaped by a world that may have been encouraged towards stability and complexity. Emergence is not accidental. It is what happens when systems operate under the right conditions for long periods. If those conditions were shaped intentionally, then human emergence is part of a larger continuum rather than a coincidence. This perspective doesn't diminish natural processes. It emphasizes them. It suggests that the earliest minds recognize that natural processes produce complexity more effectively than direct manipulation. Rather than constructing organisms, these minds might have shaped the environment so that organisms could arise on their own. This approach mirrors how ecosystems on Earth work. A forest does not grow because trees are placed manually in the soil. It grows because the environment supports growth. The earliest minds, if they guided planetary formation, might have acted like gardeners of cosmic environments. If humans emerge from such an environment, what does that make them? One answer is that humans are expressions of environmental stability. They are what happens when a planet maintains balanced conditions long enough for intelligence to evolve. They are the continuation of a process that began before planets existed. They carry the imprint of cycles set in motion long before life appeared. They represent a new form of complexity built upon older forms. This does not imply purpose, it implies connection. Another way to think about this is through the idea of inheritance. Humans inherit traits from their ancestors biologically, but they also inherit environmental structures from the planet. The length of the day influences their sleep. The tilt of the axis influences their seasons. The presence of the moon influences their tides. These environmental features shape not just behaviour, but biology itself. If those features were guided early in Earth's history, then humans inherit the results of ancient decisions, even if those decisions were subtle. This makes humans participants in a chain of influence that extends far back in time. What this means for humanity is not that they were made for a purpose. It means that they arise naturally within a framework shaped by earlier intelligence. In this context, humans might be seen as part of a larger pattern, not the final result of anything, not the central focus, simply one of many potential outcomes when conditions support complexity. Humans often wonder whether they are alone in the universe. They look for planets with oceans, atmospheres, and stability. They search for signs of life or intelligence elsewhere. If the earliest minds shaped Earth, they might have shaped other worlds too. In that case, humans might be one of many intelligent species emerging in environments shaped for complexity. This does not imply coordination. It implies possibility. A universe with guided conditions could produce intelligence in multiple locations over time. Humans would then be one expression among many. Thinking about humanity in this way shifts the question from origin to role. Humans are not observers separated from the processes that shaped their planet. They are participants who emerged from those processes. They carry biological clocks tied to cosmic cycles. They breathe air produced by ancient organisms. They build structures using materials created in earlier stars. They rely on water that has cycled through Earth for billions of years. They exist because long-term stability created opportunities for complexity to grow. Whether that stability was natural or guided, humanity is built into that continuity. If the earliest minds intended anything in shaping environments, it may not have been directed at humans specifically. It may have been directed at the emergence of complexity wherever it could arise. Complexity is valuable for intelligence. Intelligence is valuable for understanding. Understanding generates new forms of influence. In this view, humans are part of a cycle where intelligence leads to further influence, which shapes new environments, which produce new forms of intelligence. If this is true, then humans are not the end of a process. They are the continuation of one. They belong to a lineage of events that stretches back to the first structures in the early universe. They are shaped by patterns established before life existed. This perspective encourages humility rather than importance. It places humanity within a system much larger than itself. But it also emphasizes that humans carry traits that reflect the deepest patterns of the cosmos. One of those traits is curiosity. Curiosity is not merely a desire to know. It is a drive that emerges when organisms live in environments with enough stability to explore without constant threat. A stable world allows organisms to allocate energy beyond basic survival. Curiosity can become a tool for adaptation. In humans, it became a tool for understanding. If the earliest minds valued complexity, they may have recognized that environments encouraging exploration can lead to intelligence capable of perceiving larger patterns. Another trait is the ability to modify environments. Humans change landscapes, build cities, create tools, and alter ecosystems. This ability is powerful, but it comes from simpler roots. Beavers build dams, birds build nests, insects build colonies. Humans have more advanced capabilities, but the foundation is the same. If Earth was shaped by earlier intelligence, humans might represent a new branch of that process, extending influence in ways the earliest minds might have expected even without knowing the specific form it would take. Humans also possess self-awareness. They understand themselves as entities distinct from their environment. They reflect on their behavior, question their origins, and imagine possibilities. These abilities did not emerge suddenly. They developed through long evolutionary processes influenced by the environment. Self-awareness might be a natural outcome of complexity. If the earliest minds guided the conditions that support complexity, then they indirectly shape the development of self-awareness. Humans are not designed to understand the universe. They developed the capability because it increased stability and adaptation. But that capability allows them to detect patterns that hint at deeper structures. Some people interpret the existence of intelligence as evidence of purpose. Others see it as an emergent property of evolution. If Earth is engineered in a broad sense, intelligence could be both emergent and encouraged. Encouragement does not require intention towards specific outcomes. It requires creating conditions where outcomes become possible. If the earliest mind set the stage, humans stepped into that stage by following natural processes. What humans do with these capabilities is part of the question. If intelligence emerges in environments shaped for stability and complexity, new intelligence carries the potential to continue shaping environments. Humans already do this instinctively, even without understanding the deeper context. They modify weather through emissions, they influence landscapes through farming, they shape ecosystems through movement. These actions come from needs, not from intention to shape planetary systems, but they demonstrate that intelligence naturally extends influence. If the earliest minds shaped environments, humans represent the next step in that chain. This perspective also raises the question of identity. If Earth is engineered, even subtly, then humans are not isolated observers. They are expressions of a long sequence of interactions between matter, energy, environment, and intelligence. They are one of many possible outcomes. They carry the imprint of cycles that shaped their biology. Their internal clocks reflect day and night. Their bodies reflect gravity and climate. Their minds reflect the challenges solved by their ancestors. They are part of a universe shaped by patterns that existed before them. This does not reduce human uniqueness, it contextualizes it. Humans are unique in their combination of traits, but not in their participation in larger cosmic processes. If the earliest minds shaped Earth, humans are participants in a multi-layered system of influence. They are not creations in a narrow sense. They are outcomes of an environment shaped for complexity. That complexity eventually led to intelligence. Intelligence led to reflection. Reflection leads to understanding. Understanding can lead to new forms of influence. Humans might then be seen as inheritors of influence rather than recipients of design, not created with a function, but positioned in a chain where influence flows across time. The earliest minds shaped conditions. Conditions shaped life. Life shaped intelligence. Intelligence shapes environments. Humans are one link in that sequence, not at its end. When considering the possibility of a civilization so old that it existed before planets took their present form, a civilization capable of influencing matter and energy on scales humans can barely imagine, one question eventually becomes unavoidable. If such a civilization existed and left traces in the conditions that shaped Earth, why is there no clear sign of them now? Why is the universe not filled with obvious structures, messages, or movements that reveal their presence? The absence of direct evidence creates a silence that can feel final, but silence does not necessarily indicate disappearance. It can indicate change, it can indicate transition, it can indicate a shift in form or behavior beyond what younger civilizations are able to detect. The earliest minds, if they arose from the very fabric of the early universe, would not be bound by the same limitations as biological beings. They would not have lifespans measured in years. They would not rely on fragile bodies that degrade with time. Their existence might have been tied to the stability of fields, flows of energy, or structures that cannot be easily compared to anything humans know. If they changed, the change would be subtle from a biological perspective, but immense from a cosmic one. The silence that surrounds them might not be the result of disappearance. It might be the result of transformation. One explanation for the silence could be that the earliest civilization did not operate in ways that produce artifacts recognizable to younger species. Biological civilizations build structures, tools, and networks because they need them. They interact with matter using physical instruments. They leave behind objects that decay over time but remain noticeable for large spans. The earliest minds, however, if they existed as patterns within energy fields, may not have needed anything like physical structures. Their form of interaction could have been integrated into the environment itself. If they influenced matter on large scales, They might have done so without leaving behind anything that resembles technology. In that case, the silence is not a mystery. It is the expected outcome of beings whose presence was never expressed in ways familiar to biological life. They may not have built cities or machines. They may not have communicated using signals or symbols. Their influence would be measured through the stability of planetary environments or the distribution of matter in regions that later formed stars. Their signs would be indistinguishable from natural processes. The same guidance that might have shaped Earth could have been applied to countless regions without leaving any direct marker. A civilization that works with the universe rather than against it would leave behind patterns, not monuments. Another explanation is that the earliest civilization might have reached a point where further activity became unnecessary. If their goal was to encourage conditions that support complexity, once those conditions were established, continued intervention might have offered no additional benefit. A gardener who prepares soil and plants seeds does not need to remain in the garden constantly. They understand that systems are capable of developing without constant management. If the earliest minds created stable zones within the cosmos where complexity could grow, they might have withdrawn gradually. Their withdrawal would not be a disappearance. It would be a transition from active shaping to observation, or even further into a state where observation itself becomes unnecessary. Over immense spans of time, even the nature of their existence might have changed. If they were tied to structures that evolved as the universe cooled, they might have integrated into new forms of matter or energy. They might have become part of the long-term cycles that govern galaxies. Their presence could be woven into gravitational flows or magnetic structures. To a younger species observing the cosmos through telescopes, these features appear as physical laws or natural behavior. But if intelligence once influenced them, the influence is indistinguishable from the universe itself. There is also the possibility that the earliest civilization moved beyond the need for the environments they shaped. If they learned to manipulate energy and matter at fundamental levels, they might have found ways to exist independently of stars, planets, or galaxies. Their evolution could have carried them into domains where physical structures matter less than patterns within fields. Humans often picture advanced civilizations traveling between stars or building enormous structures, but advancement does not require expansion. It can require refinement. Beings who understand the universe deeply may have discovered ways to exist within forms that are invisible to younger species. This kind of transformation might have occurred gradually. As the universe cooled and expanded, the energy densities changed. The conditions that allowed early intelligence to form may have become less accessible. The first civilization might have had to adapt. Their adaptation could involve condensing into smaller regions, dispersing across larger ones, or integrating with long-lived structures such as dark matter concentrations or cosmic filaments. Their disappearance from the observable universe could be the result of moving into phases of existence humans cannot detect. Another possibility is that the earlier civilization reached limitations imposed by the universe itself. Intelligence allows beings to understand patterns, predict outcomes, and manipulate environments. But the universe has boundaries. Energy becomes less dense over time, structures become more diffuse, stars form and die, galaxies evolve. If the earliest minds relied on specific conditions, those conditions may have changed to the point that their original form of existence became unstable. In that case, their silence would be the result of the universe shifting in ways that made their continued existence difficult or impossible. However, if these beings were capable of guiding cosmic environments, they might have anticipated these shifts. They may have prepared for transition long before younger civilizations could detect any sign of them. Their transformation might not be a failure but a progression. Humans with lifespans measured in decades often think of extinction as abrupt and absolute. But a civilization existing for billions of years would think differently. Their changes might occur on timescales that appear static from a human perspective. Their silence might reflect the slow pace of evolution at cosmic scales rather than disappearance. There is also the possibility that they chose silence. If their aim was to encourage complexity across the universe, influencing younger civilizations directly might disrupt natural development. Communication, contact, or intervention could alter the path of emerging species in ways that limit their growth. Encouraging complexity is different from controlling it. If the earliest minds valued natural emergence, they might avoid contact deliberately. Their silence would be a form of respect for the autonomy of younger intelligence, rather than an indication of absence. In this view, the earliest civilization vanishing into silence is not a disappearance. It is a deliberate boundary, a decision to allow new civilizations to develop on their own terms. This perspective assigns agency without imposing purpose. It suggests that intelligence developing in multiple locations across the universe might be part of a larger pattern, but that each instance must evolve independently. Direct intervention could undermine the resilience gained through natural adaptation. A civilization that understands the value of such resilience might maintain silence indefinitely to avoid influencing the development of others. Another angle to consider is that the earliest civilization might not have vanished entirely. Instead, they might remain present in ways humans cannot detect. They may exist in forms unrecognizable to biological senses or technological instruments. If their existence depends on interactions in dimensions or fields outside the range of human measurement, their presence might be ongoing. Humans would interpret the absence of direct signals as silence, but silence might simply be the result of different modes of existence. Humans are sensitive to light, sound, and electromagnetic signals within narrow ranges. A civilization not bound by these limitations might communicate or act in ways that bypass all detectable channels. Another possibility is that the earliest minds integrated into the fabric of the universe to such a degree that their actions appear as physical laws. When observing the cosmos, humans see consistency. Gravity behaves the same everywhere. Light moves at the same speed. Particles follow predictable patterns. If the earliest civilization influenced the emergence of these patterns, or shaped aspects of them, their influence would not be distinguishable from the laws themselves. In that case, the silence is not indicative of absence. It indicates that their influence is ubiquitous and foundational. Humans interpret universal laws as natural, but if those laws were shaped early on, they represent the final legacy of a civilization that integrated completely into the underlying structure of existence. There is also the possibility of decline. Even advanced civilizations face challenges. If their existence depended on maintaining complex patterns of energy or matter, those patterns might degrade over time. Environmental conditions in the universe change. Structures break down. If the earliest minds were bound to particular configurations, they might have experienced forms of decay. Their decline would occur slowly, over spans so vast that the idea of decline itself becomes difficult to interpret. A civilization that takes millions of years to transition from stability to dissolution would appear silent to younger beings. Their final stages might be indistinguishable from background processes in the cosmos. In another scenario, the earliest civilization could have scattered. Rather than remaining concentrated in particular regions, they might have dispersed across the universe. Their dispersion could be intentional or the result of changing conditions. As energy densities decreased, maintaining cohesive structures might have become more difficult. Individual components of the civilization could have adapted independently. Their collective identity might have dissolved as parts integrated into different areas. The silence, then, would not reflect a single vanished group but countless remnants, each operating on scales or in forms that cannot be detected from Earth. Humans often imagine that advanced civilizations communicate, build, travel, or leave messages, but communication is not necessary for survival. It is a behavior shaped by social species. The earliest minds might not have been social in any familiar sense. Their interactions could have been based on merging, separating, or resonance within fields, rather than exchange of information. If they existed as distributed networks, the idea of communication as humans understand it might not apply. When such a civilization changes or disperses, it leaves behind no messages because messages were never part of its structure. There is also the possibility that the earlier civilization reached a form of comprehension so complete that continued existence in their previous form no longer served any purpose. Intelligence capable of understanding the universe might eventually seek integration rather than expansion. They might aim to become part of the processes they once observed. In this scenario, the silence reflects completion, not disappearance, but fulfillment of a trajectory that began with understanding and ended with integration. Regardless of which explanation best fits, all paths lead to a similar conclusion. If the earliest minds existed and influenced conditions that shaped Earth, their silence is not surprising. Their influence would not resemble artifacts or structures. It would resemble patterns that persist across billions of years, patterns woven into planetary formation, environmental stability, and biological rhythms, patterns that younger civilizations interpret as nature itself. From here, the story moves toward the final question. If such a civilization once existed, and if their influence helped shape Earth, what does their silence imply for the future of humanity? And what sort of legacy are humans now building within the universe's unfolding history? As the idea of the first civilization fades into the quiet distance of cosmic time, what remains is not a certainty, but a sense of continuity. The patterns carved into the universe long before Earth formed still shape the world. The rhythms that influence every organism still carry echoes of events so old that their beginnings are impossible to trace. If the earliest minds guided anything, they did so in ways that blended with natural processes so thoroughly that their influence became inseparable from the universe itself. And as humanity sits at this moment in its own history, looking back at billions of years and ahead into possibilities that stretch farther than the mind can comfortably hold, there comes a point when it becomes necessary to step back and consider what it means to be living at the edge of an ancient blueprint. The blueprint in this sense is not a document or a map. It is the collection of conditions that allowed complexity to grow. It is the stability of Earth's orbit, the resilience of its climate, the cycles that support life, and the structures that hold the planet together across immense spans of time. If those conditions were influenced early on, they form the foundation for everything that came after. Every organism, every ecosystem, every thought, every discovery exists within that framework. Humans, with their ability to observe, question and reflect, represent a continuation of that process rather than a break from it. Standing at the edge of this blueprint means recognizing that the world humans inhabit is both ancient and ongoing. The earliest influences, whether natural or guided, do not define the future. They simply make the future possible. Humanity's position is unique because it emerges at a point where the blueprint's foundations remain stable, but the next steps are not predetermined. The cycles that shaped early organisms continue, but humanity has reached a point where it can understand them, alter them, or even disrupt them. This ability carries responsibility, not because the earliest minds intended anything specific, but because influence naturally expands as complexity grows. If the first civilization vanished into silence, their departure does not leave a void. It leaves a space where others may eventually step forward. The silence is not an instruction. It is an opportunity. It allows emerging intelligence to explore without interference, to adapt without constraint, and to make choices based on its own understanding. Earth's earliest conditions may have been guided, but its later history belongs to the creatures that evolved within those conditions. Now, as humanity reflects on its place in this long chain, it stands at the threshold of becoming a civilization that influences its environment as profoundly as the earliest minds once did. This transition, however, comes with uncertainty. Humanity's tools are powerful, but understanding is still developing. People alter climate, landscape and ecosystems without fully grasping the long-term effects. They build technologies capable of reshaping their surroundings, but lack the perspective of a civilization that has existed for millions of years. The earliest minds, if they guided anything, likely did so with a patience and scope that humanity has not yet learned. Standing at the edge of the old blueprint means recognizing that influence requires understanding, and understanding requires time. Yet the silence of the first civilization suggests that influence does not always require presence. It can come in the form of subtle adjustments, early conditions, or structures that guide without controlling. Humanity might eventually learn that the most effective forms of influence are those that allow systems to develop naturally. Intervention may not require rewriting planetary conditions. It may require supporting balance, preserving stability, and recognizing the importance of cycles that took billions of years to form. In this way, the old blueprint can serve as a quiet teacher. It shows that long-term stability supports complexity. It shows that natural processes, when left to operate within balanced conditions, can produce outcomes beyond anything a single mind could predict. It shows that patience allows structures to develop that would never appear under rapid change or constant interference. These lessons are not written anywhere, but they can be observed across the history of Earth. Humans are often driven by urgency, invention, and the desire to solve problems quickly. These traits have enabled rapid advancement, but they can obscure the value of slower processes. Looking at Earth's history reveals that many of the systems supporting life took millions of years to form. Oceans required time to stabilize. Atmospheres needed cycles to balance gases. Life itself progressed from simple molecules to complex beings through gradual steps. At every stage, time was an essential component. The earliest minds, if they existed, would have understood this deeply. Their silence could reflect recognition that younger civilizations must learn at their own pace. As humanity reaches beyond Earth, exploring nearby planets, moons, and eventually other stars, it enters a phase where the blueprint becomes something it can read, rather than something it simply inhabits. It begins to understand planetary formation, stellar evolution, atmospheric chemistry, and the delicate balance that allows complexity to emerge. These understandings are steps toward becoming a civilization capable of creating stability rather than simply benefiting from it. In this context, humanity might someday stand where the earlier civilization once stood, contemplating how small initial conditions can guide entire worlds toward resilience. Not through control, but through influence applied early and gently. Not through dominance, but through understanding. The blueprint humanity inherited is ancient and vast, but it does not dictate the future. It provides the foundation for decisions made in the present. The question then becomes what humanity will do with this foundation. Will it maintain the stability that supports life? Will it learn to adjust environmental pressures with care rather than force? Will it develop technologies that align with natural cycles rather than override them? These questions reflect humanity's transition from an organism shaped by its environment to an organism capable of shaping environments. Along this transition, the silence of the earlier civilization offers a kind of reassurance. It suggests that influence can exist without control, and guidance can occur without presence. The idea of a soft goodbye arises from this understanding. If the earliest minds withdrew after shaping early conditions, their departure may not have been abrupt. It may have been gradual, the way a system stabilizes after the forces shaping it step back. Their presence would remain as long as the patterns they encouraged continue to operate. Their absence would not be emptiness, but a continuation of the natural processes they once guided. A soft goodbye implies that a civilization can complete its role without erasing itself. It can become part of the background, part of the fabric of the environment, part of the underlying structure. It can move from activity to influence, from influence to integration. If the earliest minds followed this path, their legacy persists not in artifacts but in conditions, not in messages but in cycles, not in symbols but in the stability that allows intelligence to emerge long after their departure. Humanity, in its relatively early stage of development, may struggle to understand this kind of legacy. People often seek meaning through tangible evidence or direct communication, but legacies shaped over billions of years rarely take material form. They unfold through consequences. Earth's long-term stability could be one such consequence. The emergence of intelligence could be another. If the earliest civilization said goodbye softly, humanity may never detect the moment of their departure. There would be no boundary marking when influence ended and natural evolution continued. The transition would be seamless. From humanity's perspective, the silence would seem permanent, but from the perspective of beings who experience time on cosmic scales, the silence might have occurred as part of a natural progression. At the edge of the old blueprint, humanity's task is not to decipher the intentions of beings who may never return. The task is to understand the structures inherited from them, if they existed, and to consider how those structures can inform new decisions. Standing here means recognizing that influence can span billions of years even without ongoing presence. It means acknowledging that intelligence may arise again and again in environments shaped by earlier cycles, and it means accepting that humanity is now part of that sequence. The soft goodbye of the earlier civilization does not close a chapter. It opens a space. It leaves room for new understanding, new exploration, and new forms of intelligence to take shape. The quietness of their departure encourages younger civilizations to define their own paths rather than following a predetermined course. It suggests trust in the capacity of natural processes to produce complexity without constant oversight. As humanity learns more about the universe, the edge of the old blueprint becomes clearer. It becomes apparent in the stability of Earth's rotation. It appears in the cycles of seasons. It hides within the patterns of weather, geology, and biology. The blueprint is not a rigid plan. It is a framework that supports emergence. Standing at its edge means recognizing that humanity's next steps are not bound to its origins. They represent the beginning of a new space where influence shifts from inherited patterns to intentional choices. If the earlier civilization shaped only the beginning, then humanity shapes what comes next. This shaping does not need to mirror past influence. It can take forms grounded in understanding rather than power, stability rather than dominance, patience rather than urgency. The legacy of the earliest minds, if it exists at all, would not be a message telling humanity what to do. It would be the conditions that allowed humanity to exist. Those conditions remain stable enough for new possibilities to grow. A soft goodbye is gentle rather than abrupt. It gives space rather than taking it. It acknowledges that the next steps belong to those who remain. If the first civilization made such a departure, humanity now enters a phase where it must consider how its own influence will shape the distant future. The blueprint behind humanity stretches far into the past. The blueprint ahead remains unwritten. And at this moment, standing quietly at the boundary between them, humanity is learning how to move forward without losing the stability that allowed it to emerge in the first place.